And where?
Okay. Okay. And Todd, am I still co-host?
Let me just communicate with Ryan here, Ryan.
Ah.
Okay, Ryan's confirmed that it's working.
Good morning.
Morning, Arnie. How are you?
Good.
Good morning.
Morning, Esther.
Welcome back, Marika.
Okay, Marika is co-host.
Yeah. Can someone assign me as co-host again, or am I listed as co-host?
Let's see if that's something I can do.
Right.
Do not. Let's see if I can do. Yeah.
Perfect. Thanks. Hey.
Okay, I'm co-host too. So only co-hosts get to mute everyone, probably.
Yes, that's true. Yeah. Morning, everyone. We're going to get started in 5 to 10 minutes here.
Should I put up my slide?
Yeah, you can put up your slide, and then you had typed something in the last chat box, and
Yeah,
I think we lost that, but
lost it. Okay, let me put the slide up first.
Can you all let me know if you can hear this bell, which I'm going to use?
yeah,
Yes.
that's it's very
Thank you.
pleasant.
That will be the sound.
Sounds great.
Yeah. Chat. Yes, they will. George. Trying to get our cats corralled into a different room. It's not easy. It's like 30 cats.
Right?
It's
Don't
just
wanna
like
go.
it.
They like the entertainment.
Yeah. There they are.
Like kitty.
Yeah.
So Dave, it looks like you're up at NCAR
Yeah.
about 6 months ago.
Yeah, about 6 months ago. So yeah, I took this one from the roof outside my office. So
It's a good view.
yeah, it's not a bad view, really. There's Cheryl. Hi, Cheryl.
Hello. Oh, I didn't know that there was an option for video. I just woke up.
Well, you can, that's fine. We're going to ask all the non-speakers to mute themselves nonetheless, but but we haven't got started yet.
So Todd is going to be timing my 15-minute talks. I just didn't think I could do all of the various things without a lot of anxiety. So, and we decided on about 12 minutes for the speakers for their talk. Is that correct? 12 to 13.
Yeah, I think it's up to you. We want to try to allow time for a question or two, and then at least 30 seconds to transition to the next speaker.
Right.
So
Todd, yeah, maybe somewhere around 12 or 13 minutes, or
Okay.
to just break in with a time, and I'll say something at that point.
Okay. Oh, is it okay if I ring the bell?
Yeah, I think so. We'll just let people know.
Okay. Oh, I'm going to start the recording soon. So once people are here, if you could let people know that we are recording.
Yep.
Okay.
And we can edit the beginnings and end out.
Okay.
Do we have an estimate somewhere of how many people are watching it via the YouTube feed, or
I haven't heard anything from Ryan and Elizabeth about that, but I could ask them.
I think they're keeping track of those numbers, but I don't know if it's easy for us to see it in real time.
Right.
Yeah, while you're sharing your screen, it's kind of hard to manage all of the various
Right.
things. I'm just looking for some of our speakers that are speaking this morning. I know Alex was on earlier. Oh, Olivia's here.
Yeah, Olivia's not till after the break.
Right. Yeah, there's Alex. Okay.
So we're looking for Ron Feng after Alex.
Yeah, I don't see her yet.
And Young sent us his slides, but I don't see him logged on yet. And then we do have Adam's slides, but I don't see him yet. So.
Yeah, Todd, I keep getting a message that people are waiting in the lunchtime Zoom session, I think.
Yeah, I've been getting those too. I think sometimes people just click in just to check it out or make sure the password is working.
I've kind of ignored them, so.
Yeah.
As long as they can find the main session, that's the key.
So, Dave, did someone tell them how to raise their hand? It's not easy if you're not used to Zoom. I keep forgetting myself.
Yeah, we should.
For the discussion, we have a slide that shows that. And I think for the talks, we want people to put their questions into the chat as opposed to raising their hands.
Yeah. I'll say something about that. I was going to say that there will be more instructions for how to interact during at the top of the discussion period. Just so.
And the moderator will be monitoring the chat?
Yes.
And Todd, you'll mute everyone if we start to hear people chattering in the background. I know.
Yes, I will be the bouncer.
Yeah, Elizabeth had that yesterday.
Well, there's Ron and Adam have arrived.
Okay.
Up to 28.
Yeah.
So I'm going to start right on the dot.
Yep, that's great. We are on a tight clock today.
We are. What was that?
I think that was the Google chat.
Okay.
So we should probably mute ourselves as co-hosts too. So I'm going to mute myself.
Good morning, Alex. I didn't say good morning.
Morning, Betty. How you doing?
Esther, for the 15-minute talks, it's a bell at 12.5 minutes. And then is there any like a chat warning prior to that for the speaker, like at 10 minutes?
Sure.
Well,
Yeah, maybe a
that's how
chat
we're doing for the
a warning at
5
10.
minutes.
Okay, a chat bubble at 10.
Okay.
Okay. And a bell at 12.5 minutes. And then, yeah. All right, it's 8:30, so let's get started. I'd like to welcome everyone to the joint session of the Land Ice Paleoclimate and Polar Climate Working Group. On behalf of all the other co-chairs, my name's Esther Brady. I'll be moderating the first speakers. Just a few things to get going. To encourage a welcoming environment, please abide by our code of conduct. We'll be recording this and posting later online. Please use the chat for questions to all of the speakers. If we have a minute or two during the longer talks, we may be able to read a question from the chat. But all of the speakers should try to follow up with the questioners in the chat discussion. And please use the chat discussions because it can be saved by everyone. Please unshare your screen at the end of your talk. During the talks, please mute your microphone and turn off your video just for less distraction if you wish. Also, we have a very tight schedule, so we are going to stick to the strict time limits for the talks that we've given you. The 15-minute blocks of time, the speakers will get a little chat bubble warning at about 10 minutes. And then that you may hear a bell at about 12.5 minutes to give us enough time to maybe look at read a question and transition to the next speaker. And then after this, please join us for lunchtime discussions. And there's one for every separate working group meeting. And these are to be very informal discussions. And we would like to see you there. Okay, let's move on to our first speaker, who is Alexander Thompson at the University of Michigan, who will be speaking on increases in Northern Hemisphere vegetation cover as a potential solution to the Holocene Temperature Conundrum. And I'm going to stop my share. There we go. And Alex.
All right, can you see my screen?
Yes.
Cool. I'm going into presenter mode. All right. Good morning, everyone. I'm pleased to be the first speaker of this session. I think it'll be a great morning. So like Esther said, my name is Alex Thompson. I'm a PhD candidate at the University of Michigan. And I'm going to talk about a project I've been working on that looks at Northern Hemisphere vegetation cover as a potential solution to the Holocene Temperature Conundrum. And I'm working on this with collaborators Zheng Zhu, who's going to present on something else a little later, and my advisor at Michigan, Chris Polson. Okay, so the Holocene Temperature Conundrum is this classic model proxy discrepancy shown here by this figure in Liu et al. 2014, where proxy data in the blue line since the early and middle Holocene was warmer and then cools towards the pre-industrial. But model simulations here shown by transient model simulations by the black line have shown the opposite, where they were cooler during the early and middle Holocene and then warmed to the pre-industrial. So updating the Holocene temperature proxies, a new paper came out last month with the temperature 12K temperature records. And this is important because it basically is showing the same signal of the temperature proxies. So here we can see from these different records that we have warmer temperatures in the early and middle Holocene, and then trending towards cooler temperatures to the pre-industrial. So this is just showing that with updated data, we still have this Holocene temperature conundrum. So in order to understand why we have this conundrum, we need to understand the factors that are driving both the model and the proxy signals. So when we look at the proxies, we can see that they're broadly resembling the Northern Hemisphere insolation signal, where insolation is higher during the early and middle Holocene. We can see that with both Marcotte et al. 2013, this blue line, and Kaufman et al. 2020. But then lower insolation and cooler temperatures towards the pre-industrial. We also see that the largest temperature response occurs in the Northern Hemisphere high latitudes. So that is shown by this top panel, where the Northern Hemisphere 30 degrees north to 90 degrees north shows large increases in temperature that we don't see in either the tropics or the Southern Hemisphere, as shown by the other two panels. So this is just telling us that the global temperature during the Holocene is largely driven by the temperature change in the Northern Hemisphere. So on the flip side, when we're looking at the models, these are the transient models that were used in Liu et al. 2014 to define the Holocene temperature conundrum. And here we can see that they are sensitive to greenhouse gas, orbital, and ice sheet dynamics. And we can see in the black lines for each of these model simulations, the warming trend through the Holocene. And largely these are because of increases in greenhouse gases shown by the orange lines. And also to a little bit lesser degree, the melting of ice sheets shown by the green. But in these simulations, we see that the orbital effect on temperature is fairly small. So we're not seeing this warming of the middle and early Holocene from orbital forcing. So that will come up a little later. So in thinking about this discrepancy and why it's happening, we kind of come to this question broadly of which is to blame for the discrepancy, models or the proxies. So to start off with the proxies, it's actually pretty unlikely that it's the proxies. We see that there's updated global data. This proxy record now with Kaufman 2020 represents over 1,300 individual records. So this is a very robust proxy record. We also see that it's showing a consistent result from this Marcotte 2013 on the left, and also this logical pattern somewhat following the Northern Hemisphere insolation signal. Now, this is not to say that proxies don't have their problems in themselves. There is possible bias in the proxy record towards the summer season based on the record locations, which are only about 16% of the proxy records do come from the Southern Hemisphere. So most of them are in the Northern Hemisphere. But through knowledge of the different types of proxies, there are ways to calibrate for these biases, which Kaufman 2020 does. So that leads to looking at the models where the problem more likely exists. And mostly this is because the models may be missing a mechanism for warming. As I showed a couple slides ago, we see that the orbital forcing temperature change is fairly minimal in these simulations. So if the models may be missing a mechanism that would be able to amplify this insolation signal from the Northern Hemisphere. So using this concept, a couple studies have tested this. One is Liu et al. In 2018, which completely removed global dust during the early and mid Holocene and found that this did resolve the Holocene temperature conundrum, which was a great step in the a great first step in the right direction. However, in the early middle Holocene, dust was more like 40% of the pre-industrial. So this definitely represents an overestimation of the temperature signal, but a great first step. Park et al. In 2019 also showed that in the mid-Holocene, Arctic amplification correlated to increases in global temperature. However, they used an ensemble of simulations, and even the warmest simulation that they used was still a little bit too weak to fully resolve the temperature conundrum. So these are great first steps, but we still conclude that we need to find the correct mechanism. However, I will suggest that that correct mechanism is vegetation. We know that vegetation can warm the climate through changes in albedo, as lowering albedo by adding vegetation in the Northern Hemisphere has been shown to shift the energy flux equator, as shown in this figure on the right, as well as warm the climate through transpiration effects. And vegetation checks off the key part that Northern Hemisphere vegetation can amplify that insolation signal. So vegetation is promising, as well as we know from pollen records that increased vegetation cover occurred in the early and mid-Holocene in both the African Sahara, largely known as the Green Sahara, and Northern Hemisphere high latitudes, increases in boreal forest cover. So we know that this occurred in the early and middle Holocene, so this is a good mechanism to test. So with that, in order to test this mechanism, we use fully coupled ICESM1 time slice simulations. So this shows the different time slices that we're running at, from 12 Ka to the pre-industrial at 3 Ka time slices. And at each of these time slices, we run a base simulation for 900 years with the model specs you can see on the screen, as well as we correct this for the calendar effect. So in each of these simulations, we account for the model forcings that the transient simulations in Liu et al. 2014 accounted for. So changes in greenhouse gases, these all increase throughout the Holocene, ice cover decreases, as well as changes in orbital insolation. However, we now prescribe vegetation throughout these time slice simulations to change the vegetation combinations. So at each of those time slices that I showed before, we have a simulation that includes pre-industrial conditions. So we have a desert Sahara, like we see on the left here with the bare PFT, and Arctic tundra, as we see on the right, with Arctic C3 grass. However, for each of the early and middle Holocene simulations, we run sensitivity experiments that show the Green Sahara and Arctic boreal forest expansion. Green Sahara shown on the top, and boreal tree being set to where Arctic C3 grass was set in the pre-industrial on the bottom. So this shows the sensitivity experiments where at each time slice we have a pre-industrial vegetation case, but then in the 6 and 9 Ka we add a Green Sahara, and then further add a Green Sahara and a boreal forest simulation. So to look at our results, I just want to mention that the data that I'm comparing to for this model proxy comparison is from Kaufman et al. 2020. And these lines represent a calibrated annual line in the black, which use the temperature proxies that have been confirmed to be showing an annual temperature signal. And we're calibrating to a temperature anomalies here. And then in the purple, we have calibrated temperature, but these are some of the records that are not necessarily confirmed to be an annual signal. So when we first look at the no vegetation change, so these are all the pre-industrial vegetation cases, we can confirm the Holocene temperature conundrum because we see that the proxies are showing this cooling trend, but the models are showing a warming trend. But when we add a Green Sahara here, we can see that in the 6 Ka simulation, the Green Sahara warms global mean temperatures to match very well with the calibrated annual curve from the proxies. And at 9 Ka, the addition of Green Sahara goes to within error of the proxy record, but is still a little bit cooler. So these do represent an improvement of the match with the proxy record. And then when we add boreal forest to those simulations, so now this is including a Green Sahara and a boreal forest, we can see that the 9 Ka simulation matches very well with the calibrated annual signal, as well as the 6 Ka is a little bit warmer, but is still within error of that calibrated annual signal. So we see that the temperature proxies and the models match much better now through these changes in Northern Hemisphere vegetation. So just broadly to conclude, we see that increased vegetation cover is promising as a missing mechanism in the models, and we can see that this may help resolve the Holocene temperature conundrum. And then just broadly, the importance of this is that resolving this model proxy discrepancy in the past gives us some confidence in future projections with models that we can account for this future land surface change and have more confidence when we do this, that these past models have shown that this does reduce the model proxy discrepancy. So thank you for listening, and I will take questions. I think I'll be looking in the chat for some of these.
Thank you, Alex. That was really great. And I'm looking for questions. By the way, did you see the chat bubble that the message that Todd sent? Did that pop up while you were speaking?
So the way that it works for me on when I'm sharing my screen is I have to pop the chat out myself.
Okay, we do have one question from Cheryl Harrison. Alex, do you think the new land models could adapt to changing climate and give a better match to proxy records?
If by new land models you mean some of the more recent updates like the FATES models, I would think so. I'm still learning what the capabilities of these models are, but by being able to better simulate these changes in vegetation, especially in making these dynamic vegetation models that may better capture some of these changes in vegetation so we don't need to prescribe to match with proxy records, I think this would be a great improvement on some of these cases like the Holocene temperature conundrum, definitely.
Okay, I missed an earlier question from Run Fang, who asks what drives the boreal forest retreat after the 6 Ka? Quickly, because we're really running out of time.
Yeah, I would think this is mostly related to orbital forcing and vegetation climate feedbacks. But this is something that's a great question to look deeper into some of the mechanisms. And I think we can do that with some of these simulations. Thanks, Ron.
Okay. I do see some more questions, so maybe you can answer them in the chat when you're.
Yeah, I'll answer them as we keep
when
moving.
You have time. But we should get to our next speaker. So if you can end your share. All right, our next speaker is Ran Fang from University of Connecticut, speaking on moist climate across the North Africa and subtropical Eurasia in mid-Pliocene models and proxies.
Okay. All right. Good morning, everyone. And today I would like to share with you some of the new results we gathered from analyzing mid-Pliocene simulations and proxy records, as well as some of the new simulations we have performed. So for those who aren't familiar with the mid-Pliocene, this is a period in Earth's history that we last saw a prolonged time with 400 ppm CO2. So there's a lot of international interest in studying this period to learn things about model skills in reproducing such a warm period, as well as some of the climate changes that could have implications to future climate. So this is the work that I'm working on in collaboration with Tripti, Bhattacharya at Syracuse. And some of those simulations are being performed in collaboration with Betty and Esther. And a lot of simulations that I'm using are from the Paleoclimate 2 work group. Right. So the motivation of this the study is to look at how continental hydroclimate would behave in a warm period, such as mid-Pliocene. As showing this map here from the paper by Brian O'Gorman, in RCP 8.5 scenario, the precipitation minus evaporation, the quantity that measures the net water flux to the surface, changes very differently between across the ocean and on land. So across the ocean, the change follows the classical wet gets wetter, dry gets drier paradigm. While on land, it's more complex. There are regions that in the close to the subtropics actually get wetter, and there are definitely regions, a lot of regions are getting drier. And in our new Paleoclimate 2 Pliocene modeling the comparison project phase 2 simulations, and we also see very interesting and complex hydroclimate responses across the continent. So across the North African monsoon regions, stretching all the way across the East Asia monsoon regions, we actually see a positive P-E in multi-model ensemble. And this positive P-E also shows up in the zonal mean P-E across the continent as well, as showing in this red curve here. And there are hydroclimate indicators for this time period, which is plotted on top in those filled circles. And you can see this weathening pattern stretching from North Africa to East Asia is broadly consistent with proxy hydroclimate indicators. We also calculated the pattern correlation between the proxy hydroclimate indicators and individual Paleoclimate 2 model simulations, as well as the multi-model mean, showing this plot here. The metric we used is GWATS AC. For proxy hydroclimate indicators, they're typically categorize the hydroclimate change into 3 categories: wetter, drier, or no change. So we have to do the same for model simulations. However, for model simulations, we have to come up with a classification scheme to categorize the model simulated changes as wetter, dry, and no change. And the way we're doing this is by using a threshold. So wetter would be simulated P-E changes greater than certain percentage of pre-industrial, and drier would be the percentage that lower the minus the percentage of pre-industrial, and no change would be somewhere in between. And we can calculate GWATS AC as a function of the threshold for individual models. Well, the take-home message here is that for most of the Paleoclimate 2 models, as well as the Paleoclimate 2 multi-model average, for a range of threshold, the model does seem to match the proxy data. So this pattern of wettening in the North African and the East Asian monsoon regions is robust across the model and data. And this calculation is done by Tripti at Syracuse. There are a couple hypotheses that have been raised during the past few years to explain this wettening of continent, especially across the subtropics during past warm periods. And then first one of them is this potential weakening of the Halley circulation. In a lot of past warm periods, including the mid-Pliocene, what we're seeing is this very strong amplification of warming in the polar regions this result in a very much relaxed sea surface temperature gradient. And under this very much relaxed sea surface temperature gradient, we expect to see a much weaker Halley circulation, weaker subsidence, and weaker moisture divergence from the subtropics. Another idea is that for mid-Pliocene, the proxy records of sea surface temperature shows this very much enhanced warming in the eastern equatorial Pacific. As a result, the tropical Pacific sea surface temperature shows a pattern that is mimicking the temperature changes during the El Nino event. While there's a plethora of literature studying how precipitation would respond to an El Nino event. And generally, we see a strengthening of subtropical jets, and we see a equatorial shift of storm track, which explains precipitation increases in many regions across the subtropical continents, as well as mid-latitude. And lastly, more recently, changes in the land warming pattern is also being noticed to explain a lot of hydroclimate variabilities across the land in future climate simulations. In general, the difference in the warming between the land and the ocean, and the difference between the continental interior and the coast can actually drive some of the variabilities in the simulated continental hydroclimate response. All right, so in order to investigate or quantify some of those mechanisms, how important some of those mechanisms in driving the simulated P-E changes in our simulations, we further developed the moisture budget analysis following Seeger and Henderson 2013. So we start from this general P-E budget. So P-E equals minus of the sum of temporal variability of column integrated moisture plus the divergence of integrated moisture transport. So here Q is specific humidity, U is the horizontal wind, rho is the water density, and G is, of course, gravitation acceleration. So we consider, we did two things to this equation. First, for our purpose, we're interested in comparing a pair of experiments. So we applied the small perturbation method to expand this equation. So it would quantify or it would expand the terms as a control simulation result plus a perturbation. And second, we applied the Reynolds decomposition to partition the terms into climatology and transient changes because in the Plymouth2 database, as well as our simulations, we mostly saved monthly data, which is insufficient to calculate transient changes. And we also partitioned the climatology into zoonoming and spatial variability. So for zoonoming, we use ULC bracket to represent. And for spatial variability, I used this little a or a star to represent. So this is the final equation. I will walk you through what all those terms mean from the left to the right. So first term here is changes in seasonal cycle. We're applying this mostly to focus on summer changes. Here the first change is seasonal cycle. And as it turned out, this change is very small. So we're not going to show here. And the second term is the zoonoming moisture content. Third one is changes in the zoono variability of moisture, followed by changes of zoonoming circulation here, changes in stationary wave kinetics and covering, changes in moisture content and horizontal wind. And lastly, there are two residual terms. One describes changes in surface pressure. The other one describes changes in eddy kinetics and eddy moisture transport. And those two terms are calculated as residuals, given that we don't have enough available data. And I will show you in a few minutes that they're important anyway. So we're going to focus on the CESM experiments to understand the drivers of increasing P-E in those monsoon regions of mid-Pliocene. We're going to look at those 4 sets of experiments. The first set is a mid-Pliocene simulations and a pre-industrial control. And those 2 simulations have been uploaded to the CMIP6 database. So if people are interested, you can go to ESG and download them and analyze them for your own research purpose. So for the mid-Pliocene simulations, the model featured 400 ppm CO2, mid-Pliocene topography and bathymetry, vegetation, and ice sheet followed the Climate 2 protocol. Those 3 additional sets of experiments are new and are ongoing. Hopefully we can get it right up and published and upload the data to the database as well. For the CO2 experiment, we only changed the CO2 in our experiment while everything else is set to pre-industrial. For the geography and topography change experiment, we changed the topography and bathymetry to mid-Pliocene. Oh, okay. All right. Right. Anyway, so for those 2 sets of experiment, we only changed the topography, geography, or the vegetation. Okay, this is the last important slide. So what we find is for the full mid-Pliocene simulations, it looks like the most changes in P-E can be explained by the vegetation and the ice cover changes in the experiment. CO2 actually accounts for a very small amount of change. All right, so in conclusion, well, I'm skipping the moisture budget analysis, so if you're interested, check out the slides. So just to conclude, in general, changes in simulated mid-Pliocene P-E is primarily driven by continental greening and loss of ice sheet, and the mechanism is through enhancing the moisture content of the troposphere and altering the stationary wave kinetics. And we also find an important role of heli circulation changes and El Nino-like SSTs. Right, sorry, I went over. Yeah,
that's okay. Thanks, Ren. I don't think we have time for questions, but we certainly can. You can certainly follow up in the chat with some questions, which I actually don't see at the moment. Okay. But we need to get started with our next speaker.
All right.
So if you can unshare, and our next speaker is Jean Zhu, who is speaking on can we directly estimate ECS using LGM climate reconstructions.
Thank you, Esther. I will take over.
Thank you, John.
Okay, good morning, everyone. I'm Jiang Zhu, a new project scientist at the Paleo and Polar Climate section. So today I'm trying to answer a very simple question. Can we directly estimate the equilibrium climate sensitivity using reconstructions of the last glacial maxima? So the equilibrium climate sensitivity is a metric for the global warming in response to a doubling of atmospheric CO2 concentration after accounting for fast feedback process, for example, changes in clouds, changes in water vapor, etc. ECS is an uncertain number, and the paleoclimate constraints can be used to inform ECS. One major advantage of paleoclimate constraints is that they represent real-world data with large forcing and response. However, paleo temperatures usually integrate effects across fast and slow timescales. So this timescale mismatch making it challenging to directly using this paleo approach. As a result, the Paleocene project member, they proposed this a new approach in which slow processes are treated as forcings in the calculation. For example, the changes in carbon cycle and changes in land ice sheet are treated as a forcing, and you quantify the forcing with the temperature response, you can calculate the ECS. This approach has been widely applied to different climates, including the last glacial maximum. A good calculation relies on a good knowledge of the magnitude of the LGM cooling and also knowledge of the forcings. In this regard, non-greenhouse gases are especially challenging to quantify, which I will talk about later. And also there's an implicit assumption that all the different forcing agents, they have the same efficiency in changing surface temperature. Another assumption in this calculation is that fast feedbacks are independent on slow processes. That's why you can do this timescale separation. In this study, I want to examine the last two items in a perfect model scenario in CESM 1.2. So regarding the land ice sheet forcing, I have a very simple sketch showing the figure on the right. So that's the land, ocean, and the lower LGM sea level, and the presence of LGM ice sheets. So traditionally, people have quantified the shortwave forcing associated with the albedo change. That is due to the presence of the ice sheets and the shelf exposure. From this simple sketch, you can also tell that for LGM, the long wave emission occurs at higher elevation and at colder temperature, which means a long wave radiative forcing. In addition to the radiative pathways, there are also non-radiative pathways that ice sheets can change surface temperature. It has been long known that the ice sheet can change surface wind pattern, which could potentially impact surface temperature. And also from the simple sketch, you can tell that comparing the two configurations, the definition of surface differs, which means that your surface temperature will be different without involving changes in radiation. So in light of these complications, there is actually a solution. That is that we use the concept of effective radiative forcing, and we add another term, the efficacy of the forcing, trying to measure the efficiency of different forcing agents in changing surface temperature. So to calculate the effective radiative forcing, I conduct atmosphere-only simulation with fixed pre-industrial SST. Of course, I add the LGM land ice sheet forcing in the simulation. So by definition, the top of atmosphere radiation imbalance is the effective radiative forcing in this fixed SST configuration. So here I got a number of negative 1.9 watts per meter square, which is a result of the large magnitude of shortwave cooling above ice sheets and over places with shelf exposure, and a positive long wave forcing above ice sheets. So with running the atmosphere-only model for 30 years, we have this nice spatial distribution of the forcing and a nice uncertainty. However, there is one catch here, because it's impractical to fix land surface temperature. So we have a big changes in land surface temperature over ice sheets, which contribute to a global mean of negative 1.3 degrees C, which will impact your quantification of radiative forcing. So to get rid of the effects from this land surface temperature change, I use the climate sensitivity parameter, which can be calculated from running additional slab ocean simulation, importantly using the same model, same forcing, and instead in a slab ocean configuration. So you can calculate the climate sensitivity using this equation here, and you plug the lambda here, you can get a corrected effective radiative forcing. The nice thing about this approach is that you can also easily calculate the efficacy of the forcing at the expense of two additional simulations with the doubling CO2 forcing. So basically, the idea is that you scale the sensitivity to land ice sheet forcing, you scale that by that in the WCO2 experiment. So now everything is comparable. Here are some results. For the LGM land ice sheet forcing, the effective radiative forcing is quantified to be negative 3.2 watts per meter square, and the efficacy is 1.1, so it's higher. And for the LGM greenhouse gases, the forcing is negative 2.8 watts per meter square, and the efficacy is 0.9, so it's lower. A quick comment here is that with 6 simulations with a total of 270 years, we can get a complete quantification of the forcing and the efficacy of the LGM forcing. And I think this is really cost efficient. Very importantly, these results are consistent with the concept of ECS, which only contains fast feedback processes. And these results meet the requirements of forcing feedback framework, basically the TOA energy imbalance scales with the surface temperature change. So before using these numbers to calculate ECS, let's quickly try to understand why the efficacy is not 1. So you lower the CO2, the greenhouse gas concentrations to the LGM level, you end up with a cooling forcing and a lower efficacy. In order to understand that, I quantified all the climate feedbacks, and you can see that most of the difference comes from the shortwave cloud feedback, which means that in response to the cooling forcing, the cloud feedback is less efficient in changing surface temperature, in amplifying this surface temperature. That's why you have a low efficacy. And further decompose the cloud shortwave feedback into different cloud regimes, you will find that it comes from the high latitude cloud phase feedback, which has been studied in a lot of previous studies. Next, why the efficacy from the land ice sheet is higher than 1. This is complicated, but it's very interesting. As I have talked about before, that in response to the land ice sheet forcing, we have this big adjustment over the ice sheets, so contributing to a global mean of negative 1.3. So these adjustments, that's characteristics associated with this forcing. So that's part of the explanation, basically a larger adjustments in surface temperature. And also more interestingly, you can see that there are also large magnitude cooling over the North Pacific and North Atlantic. Again, the shading is the temperature in the slab ocean simulation. And on top of the SST, I plot the wind anomalies. Importantly, this is diagnosed from the atmosphere-only simulation with the land ice sheet forcing. So in a coupled mode, this is in a coupled system, this is actually the forcing. So that is associated with the topographic effects of the land ice sheets. The nice correspondence between the two suggests some causality here. The idea is that this wind pattern can change the surface temperature through coupled feedback, for example, the wind evaporation SST feedback. And importantly, this SST pattern favors a stronger cloud feedback. That's shown in the figure on the bottom. You have a much higher cloud feedback over these regions. Altogether, they give you a larger efficiency in changing surface temperature. With that, let's do some simple calculations to see whether we can directly calculate ECS using the current knowledge we have. So we assume CESM 1.2 is a perfect model, and I make use of the fully coupled LGM simulation. Again, same model, same forcing, and has been run to equilibrium. And we know, because of this simulation, we know that the truth in LGM cooling in CESM 1.2 is 6.8 degrees C. And by conducting WCO2 experiment in slab ocean configuration, I also know that the truth in ECS is 3.6. The figure on the right shows the direct calculation, assuming different efficacy. in the forcings, you can see that no matter what you do, you will always overestimate the truth by close to 1 degree C. What is going on? It turns out that the missing piece is in the ocean dynamic effect. The top left figure shows the temperature difference between the fully coupled LGM and the pre-industrial. The bottom figure shows that in the slab ocean configuration. So there is 1.5 degrees C difference between the two. The top right figure shows the difference between the two. So you can see that by using slab ocean model, using pre-industrial ocean dynamic effects, pre-industrial Q-flux, you cannot reproduce a large magnitude of cooling over the Southern Ocean, over the Eastern Equatorial Pacific, and over the subtropics. There are also differences over Northern Hemisphere too. In the bottom figure, instead of using pre-industrial Q-flux, I pulled the Q-flux from the fully coupled LGM simulation. Now you can see that you can largely remove the difference between the fully coupled and the slab ocean configurations. So the main message here is that slow ocean dynamics can amplify LGM cooling, likely through impacting fast feedbacks, for example, sea ice and cloud feedbacks. So next, let's do another calculation. In this one, we subtract the ocean dynamic effects, which is 1.5 degrees C from the total LGM cooling. Then I get the rightmost box here, which agrees much better with the truth in the model. So a quick summary, paleoclimate contains invaluable information, but we need a model to provide quantification of the forcing and efficacy, and to explore the potential state dependence of fast feedbacks on slow processes. Thank you for your attention and questions.
You're muted, Esther.
Esther, muted.
I'm sorry. I don't see a question. Oh, wait, from Jen K. It's so cool how you're bringing in understanding of the fast and slow feedbacks.
Thanks.
Yeah. And I just have a quick question that maybe we don't have time for, but I wondered if, I know there's a lot of different ice sheet reconstructions. Have you considered uncertainties related to different ice sheets?
Yeah, I think that's certainly worth exploring.
Yeah.
Yeah, I hope I can do that in the future.
All right, we might move on to our, wait, let's see. Joshu, I'm wondering if your definition of efficacy is the same as the traditional definition.
Here I scaled the efficiency to the forcing agents to that of doubling CO2. So everything is still comparable. I think that fits my goal, and I'm not sure how different it might be from the traditional definition.
Okay.
We can talk about
I think we need to move on, John, to our next speaker, who is Adam Harrington from NCAR. And he is speaking on progress on variable resolution for polar science.
Can you see my PowerPoints, Esther?
Yes.
Great. Hello, everybody. So I'm going to be primarily talking about these Arctic and Arctic grist grids that I generated that are now a part of CSM 2.2, so anybody can run them. It's a 1/4 degree refinement over the broader Arctic, and then this grist grid just throws an 1/8 degree refinement patch over Greenland. And yesterday at the AMWG meeting, I talked more about the atmosphere response. Today, I'm just going to focus on the surface mass balance over Greenland. I just wanted to thank everybody listed here who has contributed to helping me push these through into the release and has supported me as a postdoc here. So I ran 20-year historical simulations with 6 grids in CSM that are available in CSM 2.2. We got the finite volume 2 degree, finite volume 1 degree, CAM-SE C-SLAM, which is denoted by any 30 PG3 at 1 degree. And then CAM-SE C-SLAM 1 degree with coarser resolution physics, which is denoted as, excuse me, any 30 PG2. And then obviously the 2 Arctic grids. I'm going to be running it for 20 years, from 1979 to 1998, time varying SSTs, GHGs, and aerosols. This is the FHIST comp set that runs out of the box. CLM is satellite phenology mode, so there's no carbon and nitrogen cycling. CESM is in no evolve mode, which means that CLM still uses, computes the surface mass balance at these multiple elevation classes and is used to downscale the surface mass balance to the 4-kilometer CESM grid, but it does not drive a dynamic ice sheet. And for the variable resolution grids, I wanted to spin up the snow depths and the surface mass balance from scratch. Sarah Bradley had discussed how she had done this for her LGM simulations at the last meeting, but basically what you do is you run the FHIST coupled, but you zero out the snow in the beginning of the simulation. And I fixed the boundary conditions to 1979, and I ran it for 20 years. And you have to save high frequency output from the coupler. And you use that output to force CLM offline, cycling through that 20-year forcing. And it takes about 500 years to equilibrate the snowpack. And so this is the global mean snow depths on the y-axis versus time here. And so this 500 years time to equilibration is really being dictated by the requirement that grid cells with perennial snow cover need to build up to the 10-meter snow depth cap in order to start contributing positively to the surface mass balance. Another thing that I think is relevant for cryosphere studies is prior to CSM 2.2, CLM would interpolate a finite volume 2-degree initial condition data set to your target grid at initialization. And that can be problematic if you're running at higher than 2-degree resolution. This is a global quarter-degree simulation, and it's the monthly mean snow depths for the first month of the simulation. You can clearly see the aliasing of the 2-degree grid here. And so what I did is I just ran out a global quarter-degree simulation for about 5 years, dumped out a new initial condition file for CLM, and now that is going to be used in CSM 2.2 as the initial conditions used for all the year 2000 runs. Topography and ice mass. So in order to compute consistent variable resolution topography, you define a refinement factor. So in the Arctic grist grid, it's 1 out here, and it's factor 8 in here. And that dictates the smoothing radius that you apply to the raw data set that you eventually map to your target grid, such that in the Arctic grist grid, you resolve very steep features and you have a nice looking Greenland ice sheet. Whereas if you use the smoothing radius in the coarse region over Greenland, you would have an ice sheet that looks like this. This is just what the ice mask looks like in CLM for all the different grids. Here's my only atmosphere slide. This is the streamlines at the lowest model level in a single winter. The left is the finite volume 1 degree, and the right is the Arctic grist grid. And what I like to highlight here is these reds along the steep margins, indicating you're starting to resolve katabatic drainage winds as they accelerate down these steep slopes. And this has implications for generating polynyas and then blowing away sea ice and ice melange and fjords. So in the future, that can be useful for improving the ice sheet behavior. I'm working on a visualization with Sizzle which I'm going to base it on something I stole from Dave Bromwich. I'm still here. I'm just waiting for the next slide to load. There we go. Surface mass balance in CLM is given on the top row for the 6 grids. Finite volume 2 degree to 1 degree, it looks better. PG2 to PG3 looks better. Arctic looks pretty good, and Arctic grist looks really good. You're starting to resolve, obviously, this orographic precipitation along the southeast coast and your ablation zones. And then here's RACMO for reference. And so we're starting to do pretty good. You're even getting some orographic precip over here in the Pernovic region and the Tahuli region up here. This is sort of the base of the talk now is going to be about how the downscaling seems to impact the surface mass balance. And so the downscaled CESM surface mass balance on the bottom rows, and for the coarser resolution grids, it does a good job of recreating the high resolution surface mass balance. But for high resolution, we're really starting to resolve the surface mass balance. It turns out that the downscaling degrades the skill of the surface mass balance field. It systematically lowers the ablation rates and also lowers the accumulation rates that you benefited from the high resolution. So we'll look at this a little closer. We'll look at some in situ transects. The K transect is the most popular transect in Greenland. And then this is the lesser known, I think, B transect here. And so this is just the elevation profiles in the different grids, where the black is the raw CAM topography data set, and then the different grids representation of the Greenland ice sheet topography on these transects. F19, F2, finite volume 2 degree uses a larger smoothing radius, and so it tends to extend out the ice sheet and have lower peaks, whereas F19 does a better job of capturing that steepness. PG2 and PG3 use the same smoothing radius and topography, so they have the same steepness, but it's just a matter of the number of grid cells used to capture that steepness. And you can clearly see the Arctic and Arctic risk grids are starting to capture that parabolic nature of the ice sheet. Similar story with the B transect. And so the SMB versus elevation on these transects, the top is the B transect, the bottom is the K transect. Left panel is this SMB on CLM, and then the right panel is the SMB in CESM. And the B transect tends to, it doesn't really go through an accumulation zone. It goes through various parts of the accumulation zone. I meant to say the B transect does not go through any ablation zone. It goes through different parts of the accumulation zone. So as it goes down the summit, it starts to increase accumulation rates, and then it jets out here and it goes down a little bit. So the dots are the observations, and then that final leg down to the steep margins there, you start to get these large accumulation rates associated with that orographic precipitation. And the pink and the purple are the SMBs in the Arctic and Arctic risk grids, and you're actually resolving some of that orographic precipitation. You're getting closer observations where your coarser resolution grids are not. Down here on the K transect, this light blue is the finite volume 1 degree grid. It does a decent job of getting that SMB elevation gradient, but obviously can't resolve the high melting rates and steep topography. The Arctic grid, this purple, does a decent job of getting closer to the observations. And then the Arctic risk grid, the pink curve really lines up pretty nice with the K transect observations in this region. Now, when you go to downscaling to the CESM grid, the pink Arctic risk, it actually reduces the melting rate systematically, and which is not good. But it does a great job of getting the finite volume 2 degree and 1 degree to more match the sort of elevation gradients of the SMB that you see in the observations. Similar story here where the high resolution pink and purple systematically lowers the accumulation rates when they were before pretty well lined up with the observations, where in the lower resolution regions like the blue and the light blue, it actually tends to increase the accumulation rates in this region here, where before it was a little bit too low. So just a metric of sort of the strength of the downscaling is you take the CESM topography minus the CAM topography in these different transects. And basically what it's doing in the B transect is it's going to use those higher elevation classes to do the correction. And in this case, it ends up helping bring about a better surface mass balance in both the B transect and in the K transect. The NE30 PG3 kind of gets a double bonus because you're both using lower elevation classes down here to get you higher ablation, and then higher elevation classes over here to get you better accumulation. And if you recall from here, you anomalously get this NE30PG3 does really well, and that seems to be the reason is a large correction due to the downscaling. This is a problem that is my fault. The topography used in CAM, GM TED, is systematically lower than the topography in CESM. So that's CESM minus the GM TED is this black line, and you notice there's a positive bias pretty much everywhere throughout the transects. And so even if we had the highest resolution CAM model, you're still going to activate the downscaling because of this difference. And so that needs to be fixed. I don't think I have much time, but these are the violin plots after Leo, and it's just showing the PDFs of the differences flipped on their side of the nearest grid point to an in situ observation in the LIVVT toolkit, and we break it up by the accumulation zone, blue dots, and the ablation zone blue dots, and then the white radar paths ice bridge in the accumulation zone. So that gives you 3 different plots, and it's just showing that as you go to higher resolution across here, you tend to getting smaller biases, and the PDFs are thinning out and getting closer to observations. This horizontal bar is the median. And so in this case, in the in situ accumulation zone, you're getting that median right at the 0 point. In the ablation zones, the biases are always going to be larger. You have larger melt rates, accumulation rates. I assume that's my 1 or 2 minutes warning. You go to higher resolution, you tend to do better with your accumulation rates, PG2 to PG3, and maybe, but definitely when you go to Arctic and Arctic GRIS, you really start to resolve the mass balance. And here's what it looks like on the CESM grid. And I'll just point out that you're losing that skill that you really gain from resolving the ablation zone when you go into CESM. It systematically pushes it up, whereas it really does seem to help these lower resolution grids. And lastly, I just want to talk about this high mountain Asian project for 1 minute. We want to see whether 16th of degree refinement can simulate the surface mass balance of high mountain Asian glaciers. So this is what the grid looks like. The refinement factor is 16 in here. And then I just want to point out, I've ran global quarter degree simulations, and there is no perennial snow in high mountain Asia. So this is monthly mean snow depths for each month of the year. And you can see there's no snow depths that survive the summer. And so we're hoping that resolving the topography is going to help with that. But more on that later. This is with Renee Wingard. And so I'm going to stop there because I see I'm over. If you have any questions, please let me know.
Thank you, Adam. I am looking in the chat. I do not, let's see, super exciting from Jan Lennartz. Fantastic work, Adam. And Marika says, nice to see good improvement in SMB. Do you think this improvement will also lead to improved SMB changes over time? And we need to wrap up in just a couple minutes. I think this is our only question.
Yeah, I certainly hope so, Marika. Yeah, I do. I would bet. I'll bet you $10 that it would improve it over time. How about that?
All right. Okay, so we are going to move on to our lightning talks now. I believe Jan Lennartz is the moderator for this. Jan, are you, you ready to go?
Yes, I think so.
While you're getting going, I'll just tell people what's happening. Yep. So we have a series of 5-minute talks. Jan will move the slides. Some of them will be recorded. And we won't have any time for questions. So as Jan gets the first one going, questions are going to be asked and answered in the chat only. Thank you.
Okay, everyone. So we are speeding up a little bit. And this will be a series of 7 lightning talks, each of 5 minutes. And again, as Esther mentioned, this is going to be pretty fast. Todd will also use the 1-minute reminder. There are a few recorded talks, including the first one. So I suggest we get started with Chetan Kumar Chalihal, and he's going to talk about his work on the monsoon in the LGM.
Good morning. I'm and I will be talking about the evolution of Indian monsoon. In the paleo literature, the primary focus has been on the role of orbital forcing on monsoons. In this work, we have highlighted the role of feedbacks in amplifying the orbital force. So the first objective is to identify the feedbacks and then quantify the relative role of forcings and feedbacks. So to diagnose the changes in monsoon in this simulation, we have used the energetics framework. This framework renders steam energy, precipitation minus evaporation over monsoon domain as a function of two variables, QDIV and GMS. QDIV is the net energy flux into atmosphere from the top and bottom, whereas GMS is gross moist. But over land region, contribution from surface energy fluxes is negligible, and therefore QDIV is primarily influenced by insolation and cloud radiative feedback. Gross moist stability is essentially a function of vertical profile of the moist-static energy and vertical profile of omega. We find that GMS can be expressed as a unique function of water vapor. Therefore, we now have steam energy as a function of QDIV and water. Shown in red is the evolution of steam energy over India over the last 22,000 years. It starts with very low values of about 1 mm per day. More than triples by the end of the glacier to 3.5 mm per day, and then gradually decreases across Holocene. Now, using this equation, we have identified which one of these two variables, QDIV or water vapor, was dominant during different periods. We keep water vapor fixed in the diagnostic equation and allow only QDIV to vary. This gives the green plot shown here. This suggests that QDIV drives monsoon during Holocene. The net energy flux at the top of atmosphere decreased during Holocene because of recession, and this reduces monsoon. We allow water vapor to vary while keeping QDIV constant. It gives the blue curve, and it explains all of the variations during the deglaciation. Therefore, the last 22,000 years of monsoon can be divided into two regimes depending on which one of the two was dominant, water vapor and QDIV. During deglaciation, water vapor drives monsoon, and during the Holocene, net energy flux. So here is the schematic. Insolation driving monsoon through two different pathways. During deglaciation, it drives monsoon through water vapor, and during the Holocene, it drives monsoon through energy available. This energy available at the top of atmosphere is influenced by cloud radiative feedback. We could also say that insolation, the effect of insolation on monsoon is amplified by the cloud radiative feedback. Another important factor is the influence of greenhouse gas and ice sheets, which tend to be very large during the deglaciation. These two forces do not affect energy available. They primarily affect monsoon through their influence on total column water vapor. Thank you.
Okay, thanks very much. Let's just keep on going. The next one is Clay. So Clay, you're live, I assume?
Yeah, I think that's the case.
Okay.
I can share my screen real quick.
No, I will keep on
wait.
sharing my screen.
Okay.
And you tell me when to advance slides. That's the idea here.
Okay. Okay, that works. So yeah, only a few minutes to talk here. This quick presentation is about trying to get better model proxy agreement using period appropriate vegetation changes within the model with an example for the mid-Holocene in this case. You can go ahead and advance the slide. So Alex already did a good job of presenting the mid-Holocene, so I'll skip that. But we wanted to see if a vegetated Sahara in the mid-Holocene could improve model proxy agreement, particularly in the low latitude monsoon regions where the model tends to underestimate the isotopic change. So to do this, we used the isotope-enabled version of the community Earth system model. We ran 3 experiments, pre-industrial control, a 6 Ka with greenhouse gas and orbital change only, which is known as mid-Holocene desert, and a 6 Ka with greenhouse gas orbital and a vegetated Sahara, as suggested by reconstructions known as mid-Holocene veg. And here is just a plot showing the difference in the vegetation between those experiments. All right, go ahead and advance the slide. So just jumping into the results here, in the first column, I have the mid-Holocene desert minus pre-industrial change in delta 18O precipitation for the South America and Asia regions. Each one of the circles is the change in the speleothem measured delta 18O between the mid-Holocene and the pre-industrial as well. And in the right column, I have the same experiments or the same plots with the mid-Holocene vegetated minus pre-industrial delta 18O and the same speleothem values on top. So one of the big discrepancies that had been the case for without a vegetated Sahara is underestimating the change in the delta 18O suggested by the speleothems, and you can see that on the left column here. But with the addition of a vegetated Sahara, we begin to get better model proxy agreement by getting enrichment in Central South America, and as well as more depletion into East Asia, which has been a major problem before. Go ahead and advance the slide. So we can look at this with a simple scatter plot as well. On the y-axis here, we have the model change in the delta 18O between the mid-Holocene desert and pre-industrial and the mid-Holocene vegetated and pre-industrial in blue and orange respectively. And that's compared against the speleothem change in delta 18O at the sites I showed before. And so overall, as you can see in the orange, the model with a vegetated Sahara is significantly improving these relationships, getting closer to the 1-to-1 line overall. And this improvement is due to a combination of both improved delta 18O precipitation as well as the change in temperature, which also affects the delta 18O fractionation at the speleothem. You can go ahead and advance the slide. So don't really have time to talk much about the mechanisms, but very quickly, here's precipitation changes. In the top plot is the change in precipitation between mid-Holocene desert and pre-industrial for austral summer. And you have a southward shift of the Atlantic intertropical convergence zone with the mid-Holocene orbital and greenhouse gas changes. However, in the bottom plot, with the addition of a vegetated Sahara, the austral summer ITCZ in the Atlantic actually shifts northward due to changes in interhemispheric energy balance changes. That leads to less efficient precipitation in eastern South America, leading to an enrichment signal there. All right, you can advance the slide. So looking at Northern Hemisphere summer now and trying to understand the Asian monsoon response, we get a northward shift to the intertropical convergence zone with a desert Sahara due to orbital changes in the mid-Holocene. But with a vegetated Sahara, we get an even further advancement of the ITCZ, stronger monsoon in Africa and India, and that leads to more depleted water vapor getting into Asia and eventually leading into East Asia as well. All right, so I'm out of time, I think. So that's all I have. Happy to answer any questions in the chat or by email later. Thanks.
Thanks very much, Clay. Let's move to the next presentation, which is a recorded presentation. So let me make sure everyone can see this. There we go.
Good morning, everyone. Today, I'm going to talk about dynamic effect of last glacial maximum ice sheet topography on the East Asian summer monsoon. During the last glacial maximum, the Laurentide ice sheets and the Eurasian ice sheet existed. These ice sheets can reach the height of 3 to 4 kilometers. In observational studies, the impact of ice volume on monsoon has often been thought conceptually from a simple thermodynamic view. An ice sheet retreat in the Northern Hemisphere reduces surface albedo and therefore leads to warming over the Northern Hemisphere, which will enhance the land sea thermal contrast and in turn the summer monsoon. Our model results show receding ice sheets result in a weakened ESM, with the reduced ice sheet thickness playing a major role. which is just opposite to what expected from the simple thermodynamic view. Why does this difference occur? First, let's see the ice sheet impact on ESM in the model. CESM3 at T31 resolution simulates the ESM reasonably well, with the ESM characterized by a southeasterly penetrating dip into northern China. We choose the EASM index at the summer southerly anomalies at 850 millibar average in East China, the black box here. The EASM index is calculated in experiments in a hierarchy of model configurations. The red line indicates that the EASM weakens in response to retreating ice sheets, which contains the effect of both reduced albedo and reduced ice sheet thickness. The black circles indicate that when considering the effect of reduced ice sheet thickness only, the strength of EASM shows a weakening trend similar to that in the red line, suggesting the dominant role of ice sheet topography on the ESM. In response to the removal of Northern Hemisphere ice sheet topography, we can see reduced southerlies at 850 millibar and reduced precipitation over the EASM region. Two mechanisms are implicated in the connection between the ice sheet and EASM. First is the jet shifting mechanism. The lower ice sheet topography weakens the EASM through shifting the position of the mid-latitude jet. Contours show the westerly jet at upper and lower levels. Shadings show zonal wind anomalies. The removal of Northern Hemisphere ice sheet topography leads to a northward shift of westerly jet and decreased zonal main zonal wind over the subtropics. We now focus on the mechanism of weakening EASM from the moist static energy perspective. Positive vertical advection of MSE correspond to vertical ascending motion and vice versa, because the vertical integral of the MSE stratification, partial H, partial P in the troposphere is negative. Positive horizontal moist enthalpy advection, primarily dry enthalpy advection, plays an essential role in sustaining the main rainfall band. Let's come back to the jet shifting mechanism. The reduced zonal mean westerly jet in the subtropical region leads to reduction of the dry enthalpy advection into East Asia, and in turn, a reduction of the EASM precipitation. Second is the stationary wave mechanism. The lower ice sheet topography weakens the EASM through altering Northern Hemisphere stationary waves. Shadings are added geopotential height anomalies at upper and lower levels. When ice sheet topography is removed, the upper tropospheric circulation is generated is less meandering, and an anomaly stationary wave train is generated in the mid-latitudes at 200 millibar. The wave train propagates from North America all the way to East Asia along the westerly jet waveguide. The wave propagation causes an equivalent barotropic low response over East Asia, accompanied by reduced lower tropospheric southerlies, which in turn reduces the advection of dry enthalpy and hence EASM rainfall. Our CESM3 model study suggests that receding ice sheets weaken the ESM, with ice sheet topography playing a major role. Two mechanisms are implicated in the connection between ice sheet and ESM. One is the jet shifting mechanism, and the other is the stationary wave mechanism. Thanks for listening.
Thank you very much. Thanks also for keeping to the time. We really appreciate it. Next up is Zhengju Liu from Ohio State University, who I assume is here live. Are you here, Zhengju? No? Yes?
This is Esther. I don't see him in the list here. I'm looking at Liu and also Zhengyu, and I don't see him as a participant. Can you just see if he recorded something like?
Possible. I didn't check.
Yeah.
So let me go ahead and check.
If not, we'll just skip.
Yeah.
And we'll post it, of course, with everyone else's.
Yeah. So this is
a different format.
Yes, it's a different format. Anyway, so that gives us a little bit more space in the schedule. It means that we're 2 minutes before schedule. Sorry. Okay. So I suggest we simply move on, and the next one, Nagaraju Chilukoti, also recorded their presentation. So I think I'm going to go ahead and show his presentation. And please, if you have any questions for the speakers, also those speakers that have recorded their presentation, please add them to the chat. It will be stored so we can also reach out to the speakers if they're not presently taking part in this workshop right now, but we can reach out to them with the questions. So let's go ahead and listen to the next talk.
Hi, good morning to all. My name is Nagaraj Chilukoti from NIT Rourkela, India, and Irreversible Climate Change Center, NSI University. Today I'm going to talk about MJO-like variability in the Eastern Pacific during the Pliocene. My collaborators are Professor Suni Lan and Professor Dahyun Kim. MJO is an important oscillation in the tropics, and it interacts with many weather systems globally. The many researchers found that increasing global warming has increased the phase speed and amplitude of the MJO. However, variability of the MJO in the warming environment largely unknown. In this study, we focused on the MJO variability during Pliocene, which is analog of near future climate. Global temperatures are nearly 3 to 4 degrees warmer than the present climate, and CO2 concentrations are nearly 350 to 500 ppm. So we have conducted two runs. One is the pre-industrial run and another one is the Pliocene simulations. The results are discussed in November to April peak MJO season. So this is the global mean surface temperature comparisons between the Pliocene and pre-industrial control simulation. This is the mean SST during Pliocene and PI control and their differences. We can see that during the Pliocene, tropical Eastern Pacific is much warmer than the pre-industrial, and the zonal gradient is very less. Similar temperature anomalies can be found in the surface temperature also. Rainfall difference to simulation. The most of rainfall is concentrated in Pliocene north of the equator. This figure shows the standard deviation of bandpass filtered rainfall anomalies. You can see that most of the rainfall is very less during the Pliocene in the tropics, in the Indian Ocean and Western Pacific. So similar features can observed in the variance of rainfall during the winter, in the filtered and unfiltered rainfall also. This figure shows the meridional moisture gradient difference between the two simulations. So we can observe that in the Eastern Pacific, the moisture gradient is very high during the Pliocene. However, precipitable water is more during the Pliocene compared to the pre-industrial because of warm temperatures during Pliocene. This figure shows the eastward propagation of the MJO rainfall anomalies during Pliocene, almost stationary in the Indian Ocean compared to the pre-industrial. So in the pre-industrial, it is showing that clear eastward propagation. This figure shows the eastward propagation of the MJO rainfall anomalies in the Pacific Ocean. We can see the clear eastward propagation of rainfall anomalies during Pliocene compared to the pre-industrial, which is absent in the pre-industrial. This figure shows the wave number, frequency, power spectra. So most of the power is concentrated during Pliocene 1 to 2, wave number 1 to 2. So whereas in the pre-industrial, it's spread to 1 to 5. This table shows the phase speed and wave number comparisons during Pliocene and pre-industrial control. This figure shows the normalized symmetric component of wave number, frequency, power spectra. This figure shows the composite of bandpass filter rainfall anomalies during MJO life cycles phase 1 to 8. So during Pliocene, it's very active over the Eastern Pacific, and which was absent in the pre-industrial. So in the pre-industrial, it is initiating over the Indian Ocean and disappearing in the Western Indian Ocean. So whereas the during Pliocene, so rainfall anomaly is very active over the Central and Eastern Pacific. This figure shows the MJO amplitude. In this study, MJO is active over Central and Eastern Pacific significantly, and whereas the decrease over Indian Ocean and Western Pacific. So the decrease in the zonal and meridional temperature gradient plays a crucial role in modulating the MJO variability over Eastern Pacific. We also found that MJO mostly confined to the north of the equator. Thank you.
Thank you very much.
If you have any questions and comments, kindly let me know on my email.
There we go. Okay, perfect. Super. Let's move to the second to last talk, Andreas Schmittner. And I think I saw Andreas on the call. So Andreas, are you there? Make sure you're unmuted. No? Still no?
He just disconnected, so maybe he's trying to call back.
Okay, what I suggest we take a different approach, and if Arne is online.
Seems to be back.
Andreas, are you there?
Hello, can you hear me?
Yes. Okay, perfect.
Yeah, sorry, my internet connection is really flaky this morning, so I hope that it makes it through the talk. Okay.
Okay. If you're ready, we're ready.
Okay. Yes, sure.
I hope you can see your own slides.
Yes. Thank you.
Let me know if you want me to advance.
So in this study, which we've just submitted, we are looking at the effect of AMOC strength versus depth on carbon isotopes. And for this, we use the UVic model, but it is related to a recent study with CCSM3 published by Gu et al. In this EPSL paper here on the left. And what we were interested in, initially we had published this series of simulations that you can see here in the diagonal in this AMOC depth versus AMOC strength diagrams. So this left diagonal here were the experiments we've published before, where we have looked at radiocarbon on the left and C13 on the right, and compared the model simulations with sediment data from the last glacial maximum. And our conclusion in that paper was that the weak and shallow AMOC fits the data best. That would be those simulations here around 2,400 meters AMOC depth and around 9 Sverdrups of AMOC strength. But as you can see, if we only had that diagonal line of experiments, we could not separate or distinguish between AMOC strength and AMOC depth. And
we just lost you, Andreas. Okay, that's too bad. So let's wait a few more seconds, and if Andreas doesn't come back right now, I suggest we move to Arne, and then maybe if we have time, we move back to Andreas. So let's do that, because it doesn't seem like Andreas is back. So Arne, are you online?
I'm online. Can you hear me?
Yes, perfectly. So if you are ready, we are ready. Let me know if you want to advance slides, and go ahead.
Okay, let's get started. In the present paper, I'd like to address the environmental parameters that could have contributed to the extinction of benthic foraminifera during the Paleocene-Eocene thermal maximum, also called PTM, about 55 to 56 million years ago with deep time CSM simulation, 1 degree ocean resolution as part of the DeepMap project. I want to acknowledge my co-authors and funding agencies. The microhabitat of foraminifera, hereafter named forams, depend on a critical food supply by rain of organic material, available oxygen concentration, and ocean acidification. Shown on the figure are the extinction levels of benthic forams at various IODP sites, with the largest extinction levels occurring in tropical and subtropical South Atlantic Ocean during the PTM. Next slide, please. Here shown are the global meridional overturning circulation with a dominant formation of southern component water masses due to closure of the Drake Passage, opening of the Central American Seaway, and lack of ice masses in Greenland and Antarctica. These findings are consistent with earlier studies from Uwe Mikulewicz and Ansmeyer Reimer, published in 1993. A weak and shallow ocean circulation exists in the North Atlantic Ocean. With increase in CO2 radiative forcing to PTM condition at 6 times CO2 relative to pre-industrial level, the ocean circulation mode shifts from a thermal mode with polar deep water formation to a line mode with subtropical saline deep water formation, eventually a collapse of the MOC at 12 times CO2 levels. Next slide, please. Of importance for the foraminifera extinction is the stress due to lack of food. Here shown is the primary productivity of the PTM with lower than present productivity, in particular in the subtropics, but also in the equatorial upwelling zones. The difference between the 6 times and 3 times scenarios equivalent to changes between the PTM and pre-PTM conditions suggests substantial reduction in the productivity that could have been caused by a reduced nutrient supply to the surface due to reduction of Ekman-induced upwelling and decreased overturning. Next slide, please. Next slide. Simulated bottom water at pre-PTM at 3 times CO2 levels in the South Atlantic Ocean is about 12 to 13 degrees warmer compared to present-day bottom water in this 6 times CO2 simulation. Previous slide, please. The water mass temperature increased by 4 to 5 degrees Celsius relative to the 3 times CO2 simulation agreement with Paleoproxies. Dissolved oxygen declined about 20 to 25% due to reduced solubility and ventilation of the deep sea. And then the final slide, next slide, please. Calcareous forum shells also be affected by the predicted increase in ocean acidification due to the increase in PCO2 by about 840 ppmv. The simulated increase is consistent to observed rise in the lysokine inferred by Jim Zachos, our lower left figure, and estimates by Don Penman at our lower right figure. In summary, the decline of forum diversity at the PTM could have been caused by warming, stratification, a reduced food supply, deoxygenation, and increased acidification. I'm happy to take questions at the chat. Thank you.
Thank you very much, Anna. So please let those questions come in through the chat. Andreas, are you there again?
Yes, but
okay. So
I'm not confident about my internet connection.
Okay. You have approximately 3 minutes left, if that's okay.
Oh, sure.
So please go ahead or continue.
Yeah, I'm not sure really how much you could understand what I was talking earlier, but so we had these correlated experiments in this diagonal here, and then we were where we evaluated the circulation in terms of C13 on the right and radiocarbon on the left, and we found the circulation with a shallow and weak AMOC would fit the LGM data the best. But we could not distinguish, having only this diagonal between AMOC depth and AMOC strength. So Juan did these additional experiments here that go towards the right, and where we can now fill in this two-dimensional phase space of AMOC depth and AMOC strength. And as you can see, hopefully, that the errors here, the isolines of the errors are horizontal. So that essentially tells us that the carbon isotopes, both C13 and radiocarbon, are mostly sensitive to AMOC depth and not to AMOC strength, which is plotted on the horizontal here. So that is kind of the main takeaway from the study, and it is consistent with this recently published paper using CCSM3 by Gu et al., where they used 3 simulations with CCSM3 that I indicated here, the pre-industrial control LGM and LGM hosing run, where they also found that both LGM runs, which had similar AMOC depth but different strength, had very similar C13 and radiocarbon distributions, and therefore it was difficult to distinguish between those. And so we have now filled in that phase space a little bit more, and we are coming to essentially the same conclusion. And in the paper we go on, and can I have the next slide, please? And look a little bit more into the reasons for that. So this one here in the top shows the effect of AMOC strengthening. So we picked 2 experiments from the previous 2 phase space that have a similar AMOC depth, 1.9 kilometers, but different strength, 14 versus 7 Sverdrups. And there you can see in the left, the C13 difference in the Atlantic and in the Pacific. So in this, you can see here, there's increases. So an AMOC strengthening increases this southward advection of high C13 at that depth of North Atlantic deep water, which in this case is 1.9 kilometers. So you can see this higher values here. And then lower values in the upper Indian and North Pacific Oceans, and also in the upper South Atlantic. And on the right is the radiocarbon, and there you can see slightly lower values in the deep ocean, and both are correlated. So radiocarbon and C13 distributions are correlated here, and the amplitudes are relatively small compared to the deepening, which is shown in the lower panels here, surrounded by this magenta frame. Much higher anomalies in the deep Atlantic, particularly of more than 1 per mil, due to the deepening. And so that kind of explains why the AMOC depth is much more sensitive, or carbon isotopes are much more sensitive to AMOC depth changes compared to AMOC strength changes, as shown in the upper panels. Yes, and maybe
we need to stop there.
Okay. Yeah.
Sorry
Thanks.
about that. Okay. Super. Thanks very much, everyone participating in this session. What we will do now in the schedule is a small break. We're a little bit delayed, but not much. So we will start again at 15 past the hour. So in approximately 8 minutes. So please join us again for the discussion, which will be led by Günter Legge and Marika Holland. Thank you very much.
could remember.
Okay, Marika and Gunter, are you guys ready to go?
I am ready when you are.
All right, me too. So Gunter, do you want me to share the discussion slides or did you want to do that?
Why don't you do it because you have all the slides at once, so.
Okay, I will put the slides up now and let's see. All right, are you able to see my slides? Yeah. Okay.
It's not in it's not in show mode. There you go. Great.
Yeah, so so welcome back after that very short break and a lot of great talks this morning. So we are gonna now have a brief discussion and just to get started, I just wanted to let everyone know how we're going to do this. So in terms of participating in the discussion, because there's quite a few of us on the call, if you could raise your hand and then we will call on you. So this shows how to raise your hand. So basically from the Zoom window, you can click on participants, which should be at the bottom of your screen. And then from the participant window, there's a raise hand feature. And so you should be able to just click on that, your hand will show up and we should be able to see you. So I was actually planning to do the checking of hands, but it's a little hard for me because I've got my slides sharing. So Gunter, you might have to look at that.
I can help you out too.
Okay, and Dave too. Thanks. So just again, our code of conduct, and everybody be constructive and considerate in their feedback and their discussion items. And so Gunter was going to lead a discussion on the CESM tutorial. And so I will leave it to Gunter to take this.
Yeah, thanks, Marika. So good morning, everybody. Thanks for tuning in for this workshop. It's great to see so many participants. And we wanted to, so the CSM Tutorial Committee is a committee who organizes CSM tutorial that takes place at the first full week of August every year and provides the opportunity for people who want to know how to run CSM to come to NCAR when time's allowed to come to NCAR and learn about it, and also meet with scientists and with all the students there. And because of the situation here, this year, the CSM tutorial committee had to rethink on how we could provide this opportunity, and we had no other choice but to provide it fully remotely, similar to what this workshop is being held right now. And for this reason, we're only accepting half of the population of students that we typically do, and this year is going to be about 40 students. And as we were planning all of this year's tutorial, we were thinking about maybe it could also be a good time to rethink the way we actually do the tutorial. And we would really like to have the input of the community on how the tutorial could evolve from now. And so there are 5 questions listed here, which I would love, the entire tutorial committee would love to get your feedback on. And I'm just going to read them out loud and then wait for some of your comments. So what should the purpose of the tutorial be? So typically there are lectures and then practical session with labs and interaction with scientists and participants in different working groups. Should there be early career focus activities during the annual CSM workshops, including tutorial activities? Is the timing of the tutorial adequate? It's always the first full week of August, or should other time be considered? For example, paired with a workshop to boost overall attendance, for example. Does the current format of CSM tutorial work? Are there changes the community would like to see implemented? And what is the target audience for the tutorial? Either international, national, a different type of institution, and so on. So if we could hear from you and what you would expect from us to do, even to do better, that would be great. So I'll leave it, I'll open up for discussion.
Crickets.
And if everything is perfect, you like it the way it is, that's fine for you as well.
Well, I'll get it going. We raised the same question in the ocean model working group yesterday, and there was a woman on there, Lily Jones, I believe, and she was from South Dakota and worked very closely with the Native Americans there and educational programs there. And so one of her comments, and I don't see Lily on here, so you can, if she was here, she could correct me. But I mean, I think one of the concerns was about the sort of level of the material and, not accepting undergraduates. And so is there thought by the current tutorial committee about, sort of opening it up a little bit more and, thoughts about continued online presence too, to make it easier for maybe those people who can't travel to Boulder? So anyway, I just thought I'd get the ball rolling with that.
Hey, I have an idea. This is Ute. Hi, David. I'm thinking perhaps one should have something like a Jupyter script so people can learn at their own pace, and then some sort of higher level of interaction to ask questions. So that might work both for people who have some experience with other models and just want to switch over but don't want to dedicate the entire week, especially if it's remote. And then, but then there should be people around who are willing to answer those people's questions in case they do get stuck. So there's a bit of a lower threshold. I'm thinking mostly of students who want to get into modeling. And then they can ask questions from people who have run the model before. And likewise, on sort of the spectrum of people you've just mentioned, those people could work slower, getting themselves into whatever scripting and perhaps take 2 weeks if they need, and so forth. So that would sort of make it a bit more adaptable. What do you think?
So I'm going to answer this by saying first that all of the material of the tutorial every given year is online, and everyone can access it. And so it means that all the lectures that are being held at NCOM Lab are online, like the full lectures. The same with the practical sessions, but the same with all the lab exercises. So what you only need to learn really at your own pace is an account on Cheyenne in order to run Cheyenne and do the exercises. And then maybe what we could do is to have a link of contact people where those students could contact persons to ask their questions. And maybe that could be a good thing too. Regarding the level of material, I understand this could be an issue. And that's the problem here is that the advanced graduate students who need CSM for their project, or even early career scientists that are way more advanced. And so bringing the lectures at the level of undergraduate students, some undergraduate students digest the material just fine. I cannot guarantee it's the same for everyone. And yeah, that's I don't know on top of my head how to do this.
Right. I'll also highlight that we have it in the form of a comment, like a med-ed module from Comet as well. And it's a little more interactive. There's like some quiz stuff with it and things like that. But actually, Bronwyn typed something in the chat box. Do you want to go ahead and speak up, Bronwyn?
Please do.
I can speak, but there's a tree trimming situation. So yeah, so I was just saying that to me, as someone who did the tutorial many years ago, it's a really unique offering that just doesn't exist from other modeling centers, and it just doesn't exist generally for students and postdocs who don't have, who have coding experience but don't have experience running a GCM. And I've recommended basically every young scientist I work with who wants to start running CESM, I've recommended that they apply to the workshop, and I'll continue doing so basically forever. And I think it's really important to keep offering it at that level for students who are ready to sink their teeth in but need kind of a primer on how some of the different components of the model works. I mean, I think it's just so useful. The other thing, if there are changes to the format that I would really recommend trying to keep as well as possible is the networking aspect, which I know is hard to do virtually, but I met so many mentors and friends and colleagues at the tutorial years ago, and they're still part of my network today, and I don't know where I would be without that. So definitely, if it's possible to keep that moving forward, I think that's really important.
Yeah, thanks. And we've received many concern about the online version because of the lack of networking. That is definitely a concern, yes.
I wanted to add, thank you for having the distance learning course. I have both an undergraduate computer science research assistant and a beginning graduate student who I'm planning having to do this over the next few months. And I'm happy to give feedback if it's helpful. Just let me know where to direct that, and we'll see how that goes. But it is really great to have that distance learning module, not to discount what Bronwyn said at all. I think it would be really great for them if there was some kind of way to network as well while they're doing this remotely during this time. So a +1 for both the distance learning and having everything available, and for figuring out a way to keep the networking going despite the pandemic.
Excellent. Yeah. And definitely once your students have had a chance to go through that comment module, we would very much welcome the feedback on that, because, you know, we want to understand, is it the right level? You know, can they do it at their own pace where they're happy? But I think you're right. The missing piece is that interaction with the individuals as a part of that. Yeah.
Well, but also the mentoring if they get stuck, like
yes.
was saying. I think both of those are really important pieces of this. I mean, I'm connected enough that I can get them help on. We can figure things out, but if I don't know it, but for people without that connection, it would be really difficult.
Right. Alice has her hand up.
So thanks for all the feedback, everyone. So it sounds like networking is really important, which is something we suspected. Would it then make sense would people like the idea of potentially saying, like, before you come, we expect you to watch the lectures online, and then the in-person part would be more like focused on, you know, the actual labs and networking and building connections? Or do you think that having the lectures as part of that week is an important part of the tutorial?
I'll just say having sat in on the CESM tutorial and the lectures, one thing that really struck me is during those lectures, the questions that the students asked and how just like bleeding edge, like great ideas they were. And I think like you're missing that interaction between the scientists and the students as well. Just that's my quick observation.
So
go ahead. Sorry.
I'm going to follow up on this, and yeah, what we thought for this year, we thought it would be tedious to have students sit through all the lectures remotely. That's why we're asking them to watch them online. But what we're going to do, we're going to have a question and answer session for about 40 minutes with a panel of scientists where they could ask whatever question they want on the specific topic that the panel is expert in. And so this might be something we could adopt, and so that students would not sit through like 4 hours of lectures every day during a week. I don't know how students feel about all those lectures, intensive lectures during the entire week.
Yeah, I mean, from the feedback that I've seen in the past, they feel like it's just so much material and they would rather be doing the hands-on stuff a lot of the time. And I think the problem is, shockingly, that there are people who are interested in the atmosphere who might not want to pay attention during the sea ice lecture, you know? So I think it's a nice idea if they can sort of do the lectures they want at their own pace, maybe.
I'll say, though, that I also think there's value in getting that whole system. I mean, CESM is very complicated, but at least during the tutorial, you get a sense of that, how complicated it is, and that, you know, you get a little bit, even if your expertise is in sea ice, you have some sense of what the atmosphere is doing, the ocean model's doing, et cetera. So there's some balance there that is hard to meet everybody's needs, but I think there is value in having that very comprehensive overview of the entire model. So I wanted to bring up another question, which is, it's not exactly on the tutorial, but it's related. You know, we've had additional tutorials. So there's the main CESM tutorial, but then there's been polar modeling workshops. There's a CLM tutorial. So component model tutorials. And I wanted to get a sense from the participants on the line about the value of those additional activities, because it's hard to manage all of these different things. I mean, of course, there's a lot of time that goes into putting these tutorials together, but I know some of the people online have participated in some of these other tutorials. Do you think that they're worth continuing? Yeah, just see if anybody has any thoughts about that as well.
Yeah, I'm seeing in the chat window too, there's not much. We're not really advertising the comment site very well, apparently. So, so definitely more work there. But yeah, I don't know, as Marika said though, is there other thoughts about these special sort of more focused workshops and things like that, like these polar workshops? We had a size tutorial earlier this year as well.
So Alex raised her hand. So Alex.
Oh yeah.
Yeah, I mean, I haven't attended them, but I think those specialized ones are probably even at least equally or even more important for networking opportunities, because it really brings together people who are like getting started at in the same general field, and I think they're really useful from what I've heard from students who have attended them, and so I think they're really valuable. They should, yeah, it's not a substitute for the other CSM workshop, but I think what's worked well in the past is having that, like the polar one right after the CSM tutorial, so you don't have to duplicate the things like, okay, how do we run the model, but can then focus in a little bit more. And maybe that can be coupled with doing it online. I haven't looked at the Comet stuff, but that could be it too. Maybe that's a good starting point too for people to do that before they come for these specialized workshops. And then they have that in-person, like maybe a catch-up day where they can ask all the questions where they got stuck or that kind of thing. So.
Yeah.
I think, Tyler, you had your hand up.
Yeah, so I went to the polar modeling workshop in 2018, and I at no point did I ever, you know, like I did the 2 weeks where the first week was the CSM tutorial, and then the polar modeling workshop, and I never found any of the material to be repetitive, and I actually really liked getting a comprehensive overview of the CSM, and then being able to break off with, you know, other polar scientists that, you know, I keep in touch with still to this day. And so, yeah, I thought it was, the fact that it immediately followed was good, and it was just a really good experience.
Good to hear. Thank you.
Yeah, thanks.
So I know we're kind of running out of time for the discussion, and I think we're supposed to move on to talks. The next one starting right now, I believe. So so if you have any further thoughts, I think Gunter is doing an awesome job at accumulating all this input and really leading the charge in how to revamp the tutorial. So I'd suggest getting in touch with him. And we also did want to talk a little bit about joint experiments across the working groups. I think we didn't really have enough time for that during this discussion. If you're interested in some joint experiments across the land ice, the paleoclimate, and the polar climate working groups, please send an email to one of the co-chairs, because we're thinking we probably will have some more discussion of that later this summer, and we'd love to involve the community in that. So send an email to one of us and we'll put you on the list for a further discussion somewhere, you know, a month or so off. So with that, Gunter, I don't know, do you have anything final you wanted to say before we move on?
I just want to say thank you for the comments, and yes, keep them coming. I want to say personally, I always felt like we could do something during the CSM workshop since people are already there. And more importantly, if you have students that went to the CSM tutorial, please try to motivate them to come to the CSM workshop to improve their networking with other NCAR scientists and scientists from all of the other organizations that are collaborators with NCAR. So I'll leave it at that.
Great. Okay, so I think we are now going to move on to our set of talks. And so the first person up is Hannah Czrzanowski. And Hannah, I think that you can share your slides and unmute yourself. And just so everyone knows how this is going to work, at 10 minutes into your talk, I'm going to say that you have 2 minutes left. So I'm just going to talk over you and say 2 minutes. and then you should, spend a couple minutes finishing up so that we have some times for questions and to transition to the next speaker. Yeah. So Hannah, I will let you take it away. I think we can all see your slides. So.
Okay, great. I have presenter view on. You guys can't see that, right?
I think we can see your presenter view, honestly.
Yeah, we can see your presenter view.
Perfect. I can just change that.
Okay.
We don't really need presenter view. So now everything, you can see everything normally.
Looks good.
Okay, great. All right, so today I'm going to be talking to you guys about Arctic freshwater storage and export in CMIP6 models. This is work I've been doing with Marika Holland at NCAR and then Alex Jan at CU as part of INSTAR as well. So, oh goodness, okay. So just to start out, if you don't know, the Arctic is one of the fastest changing regions on the planet. I have a couple figures here on the left showing a couple of ways in which the Arctic is changing. It's by no means an exhaustive list, but the easiest one to kind of focus on is the figure up here at the top, which is the decline in Arctic sea ice extent from 1980 to sort of 2019, I think. So you see this sort of very, very strong decline there. Another way in which the Arctic is changing is river discharge. This is for Eurasian rivers and North American rivers from about 1940 to about 2020. And you see this sort of increase in the discharge into the Arctic region. And so I'm showing you kind of both of these figures today because they impact freshwater within the Arctic itself. And so there's many ways in which freshwater moves around the Arctic and which is transported. And these are kind of a figure over here on the right showing you the mechanisms by which freshwater moves around within the Arctic system. So you've got things like ice transport coming in and out of some of these straits. You've got ocean transport as well. There's atmospheric transport in and out of the Arctic, precipitation, evaporation, and then of course there's riverine inputs as well. And so it's actually a really incredibly complex system. And of course, it's not actually just detached from the rest of the world, even though we know that it's very far in the north, it impacts, has sort of global impact. So that's why we want to study the freshwater in this region. So for me, what I'm trying to figure out here, I really just want to understand what the state of Arctic freshwater storage and fluxes are in the CMIP6 models and how this is going to change in the future. So the goal here is to characterize CMIP6 model Arctic freshwater storage and export during the end of the 20th and the 21st centuries. And to do that, I'm going to compare all models from the CMIP6 suite of models that have at least 10 ensemble members for their historical simulation, and that actually provide me the relevant variables on ESGF. And believe it or not, that is a larger constraint than you maybe would think. So for the CMIP6 simulations, I'll be looking at the historical period. Technically, this goes from 1850 to 2015, but when I'm looking at averages, I'll be looking at 1980 to 2000. And then some of these future scenarios, which are defined by the shared socioeconomic pathways, I'll just be looking at 2 of these, SSP 1-2.6 and 5-8.5. The number here that you maybe want to focus on is the number to the right of the dash, which is just the radiative forcing at the end of the 21st century. So 2.6 watts per meter squared and 8.5 watts per meter squared. So to calculate storage, one of the ways you can do that is to kind of cast it in or freshwater storage is to cast it in terms of basically the amount of salinity that's in the Arctic. So what I do here is I pick a reference salinity. In this case, it's 34.8. This is often what's used for observations. You calculate the amount of, you just take the actual salinity that you have and you look at what the salinity is relative to that. So anything sort of above or below that is going to give you fresh water or not fresh water. And so in order to make sure that this term always stays positive so that your volumes are positive, you only integrate this down to the depth of this 34.8 isohaline. Now, export is sort of similar. This is import or export. It's just volume fluxes in and out of the Arctic. So instead, you just have a velocity here, a velocity term here attached to that sort of reference salinity value, this sort of salinity variation. And then you just integrate this through these vertical sections through these various passageways within the Arctic. So Fram Strait, Nares, Bering, and then storage, of course, is calculated anywhere within this region within the Arctic. So moving on, I'm going to start by showing you sort of what the model freshwater storage looks like over the historical period in 7 of these different models that actually have all of the constraints that I needed. So for everybody, for reference, if you're looking at CSM2, it's always going to be, these are always going to be in alphabetical order. So for figures like this, it's going to be second from the bottom or second from the left. So these are actually box and whisker plots that I'm showing here. There's solid storage and liquid storage. This vertical magenta line here is the observations. So this is averaged over 1982,000. You're looking at all these different ensemble members, which are, this is the number of ensemble members that each of these models have for the historical period. So what you're kind of seeing here is that we're, you know, kind of all over the map. Sometimes somebody gets the storage, the solid or the liquid storage pretty well. But again, not surprising, they're quite variable across models. Now you can also look at how these, the storage then changes in the future. What we end up seeing here on the left is ensemble. This is ensemble mean freshwater storage. So this is the mean of all the ensemble members for each of these simulations, historical in gray, shared socioeconomic pathway 1-2.6 in the Navy and 585 in the sort of yellow color here. And so this is kind of how these across models, how these different storage terms change. So we have solid, freshwater storage, liquid, and then the total. And what you see for the solid storage, of course, across all these models, it declines. And then the liquid freshwater storage typically increases. Now, how do we actually kind of get there? You can kind of look at the time evolution in this figure on the right. So this is now multi-model mean freshwater storage. I am just taking one ensemble member from each of the models in this figure, and I'm averaging it. So this is an average of 7 different models to get these lines here. So the gray is just that historical period, and then the SSPs again are 2.6 in blue, and then 8.5 in the yellow color, and that's consistent across this talk here. So what you see is this very strong decline in the solid storage, and then kind of an increase in the liquid storage as well. And the envelopes are just the maximum or minimum value that any of the ensemble members attain over that period. So you can also look at historical solid freshwater fluxes, and these are now the fluxes through these straits. So for reference, there's always a map down here for you. The sign convention is such that positives are into the Arctic for fluxes, negatives out of the Arctic. Again, what I have, the vertical magenta lines are compared to observations over the 1982,000 period. And now these gray sort of shading regions are when the observations actually had an error associated with them. So it's plus or minus that error. And so again, you're seeing this kind of really large spread in the models. Do note that some of the size of the actual spreads themselves are related to how many ensemble members are within each model. And you also cannot compare across these straits because they're very different sizes of fluxes. So typically we're all over the map again. Sometimes somebody's kind of getting something right every once in a while, but for the solid fluxes, the models don't tend, they try to get close to observations, but again, they're kind of all over the place. And so if you, again, want to look at what happens in the future, so now I'm showing these fluxes through all these different straits, and then the total fluxes down here across by adding up all these 5 gateways together. Again, this is across models, and so CSM2 here is always in a second from the right. You get this really strong decline in the solid freshwater fluxes. And so that's kind of consistent with what we saw in the decrease in storage. The fluxes out of these gateways also decline, and it's much typically stronger for SSP 585 than it is for 1-2.6. Same sort of thing, you can plot this as a time series instead. So this is now the multi-model mean solid freshwater flux through all of these different straits over these periods. And again, all of these are slowly trending toward 0, basically. So that's that very strong shift. And so it's kind of nice that the models at least all agree on that. Historical liquid freshwater fluxes also really vary widely across the models. Once again, we're going back to this historical period, 1980 to 2000, through these various straits. Doing a little bit better in the Bering Strait, although I think that maybe because I think a lot of these models may be tuned. But overall, I'd say the models seem to be getting at least closer to doing the liquid fluxes through these straits compared to observations. For example, though, in Barrow Strait, everybody underestimates the obs, but IPSL seems to at least cross the observations in at least 4 of these regions. So that's doing pretty well. If you want to look then at the future, of course, these liquid fluxes show increased freshwater export basically everywhere except for Bering Strait and the Barents Sea. So Bering Strait kind of remains fairly stable. There are some increases depending on the model that you're looking at. Do note again that these axes are quite different. So largely everything's driven by Fram Strait to some degree. And then when you look at the Barents Sea, you actually see this interesting sort of reversal in sign of the flux. Now that does not mean that the velocity of, or that the current itself has changed direction, but it actually has to do with the changing salinity, which I'll show you in
2 minutes.
a few minutes. Okay, cool, awesome, almost there. All right, so future liquid fluxes, of course, showed this increased export, like I'm saying. Bering Strait remains relatively stable over this period, but then you have this sort of transition to the Barents Sea in sort of a change in sign of that flux. And so what I wanted to do was figure out what is actually happening there in the Barents Sea. So I've done a multi-model mean liquid freshwater flux decomposition, and that's where you just kind of decompose the anomalous fluxes into their volume and their salinity components. So the darker colors here are for 1-2.6, lighter colors are for 585, and purple is for volume and green is for salinity. And when you look at the Barents Sea, what you end up seeing is that what's driving that entire change in the fluxes is entirely due to salinity rather than changes in the volume. So again, you're not getting a reversal of the current, you're actually just getting a change in the salinity and a very strong freshening, which leads to sort of import into the Arctic overall. And then you can also see why Bering remains stable, largely because these are compensating errors. So I'm going to just leave it with the conclusions here. And if I'll just take questions since I think I'm running out of time.
Thanks, Hannah. So questions for Hannah. So from
sharing.
John Lennertz, can you comment on the potential role of green?
Thank you for the question mark. Sure, I'm sure it matters, although I don't know to what degree these models do freshwater fluxes from Greenland particularly well, Jan. So that's a little bit hard for me to say. One of the things I am going to be doing, or I'm in the process of doing, is calculating fluxes out of Davis Strait. And so in that case, I think we're going to see probably a pretty strong impact on Greenland in these. But again, I think with a lot of these models, Greenland is not really where it needs to be in terms of, doing the fluxes properly. So it may play a pretty large role. So yes, we totally should talk more if I am interested in that.
I think Dave Bailey also had a question. Since the CESM and possibly other models only have 2 channels in the Canadian Arctic archipelago, do you think this impacts the comparison of fluxes with observations?
Yes. So to be fair, I do have the observations I'm comparing it to are actually from observations in those 2 particular straits, but I do think that does matter just because the way in which we have the way in which we sort of simulate these channels. So yes.
All right, so I think we need to follow on to the next talk. So if you have more questions for Hannah, please put them in the chat and we can do it that way. We've had a really great chat discussion, I have to say. So we will move on to the next talk, which is from Alexandre Adet from the University of Toronto, talking about some results from the PA MIP experiments. So great, we can see your slides and take it away as long as you're unmuted.
Okay, can you hear me?
Yep, sounds good.
All right,
so I'll give you a 10-minute, 2 minutes after 10 minutes of talk.
Perfect, thank you. Right, so today I'll be talking to you about the opposite responses of the dry and moist heat transport into the Arctic due to sea ice loss and sea surface warming in the polar amplification MIP experiments. So those, just first a bit of background. So because of the differential heating that we get from the sun on the Earth, we need heat transport to compensate for that from the equator towards the poles in both directions. And most of that heat transport, at least in the mid-latitude, is achieved by the atmosphere, here in the top panel, shown by the solid line here. And a large part of that is accomplished by the eddies, and most of that by transit eddies, which are strongly linked to the meridional temperature gradient. As you can see here, the dashed line is the eddy heat transport, which makes up for almost all of the polar heat transport by the atmosphere. So yeah, as I said, I'm using the PMIP experiments from 6 different models that were able to provide the variables I needed on the adequate frequency. And I used 3 experiments from the PMIP protocol: a year 2000 control, and future Arctic sea ice conditions, and future sea surface temperature conditions. And all of these experiments are AMIP simulations. So no coupling with the ocean or sea ice. It's just prescribed sea ice and prescribed sea surface temperature. So let's dig into the surface response to those PMIP forcings. So I'm looking at the moist static energy response and dry static energy response as well, to see what is the effect of moisture as well in the polar heat transport response. So in response to sea ice loss here in panel B, what you can see is in red, the moist static energy response, and the dry static energy response in blue, with the intermodal spread shown here in the shading. What we see here is basically polar amplification, and it is mostly due to an increase in temperature, as moisture doesn't play a large role here in the Arctic. But in response to sea surface temperature increase, we have a tropically amplified response due to the sensitivity of moisture to temperature increase in the tropics. And one thing that we see is that the agreement between the models is much better in response to sea surface warming compared to sea ice loss. There's much more variability here in response to sea ice loss. Then if we look at the MSC and DSC gradient, which are linked to the eddy heat flux, what we have, basically it's the gradient of panel B and C shown in panel E and F. So we've got a weakening of the climatological gradient, which we could expect from that a weakening of the eddy polar heat transport. Previous studies have associated the a weakening in the MSC gradient to weakening in polar heat transport. And then in response to sea surface temperature, we've got a strengthening of this gradient over the whole hemisphere, mostly, except near the poles. Yeah, so, and indeed, this polar heat transport decreases in response to sea ice loss here in panel B. So basically, we've got a reduction in the eddy polar heat transport that is mostly coming from a reduction in dry static energy transport. Because again, moisture doesn't play a large role at these latitudes. And then in response to sea surface temperature, we've got this increase here of eddy polar heat transport for MSC, and a decrease in the around 30 degrees north for the DSC transport. So moisture plays a very large role in these latitudes for the heat transport. Another thing to note is that the spread between the models is now smaller in response to sea ice loss compared to the response to sea surface warming. So that leads us to ask the questions about, like, what is exactly the role of the and how is this weakening in polar heat transport accomplished by the weakening of the gradient that we saw here? Is that link very as strong, and what is the mechanism between that? So to do that, we use a different approach compared to what we did before, as just integrating the eddy heat flux. What we'll do is, for every vertical level, longitude and time step, we will take a dry static energy pair with the meridional wind, as is shown here in this panel. So with pressure and dry static energy on the x-axis, we've got the meridional wind shown in the shading. Red is positive, so northward, and blue is negative, southward. And we can do that as well with moist static energy. Here's just DSC for an example. And what is in between those two, this those two regions, the red and blue region, is the zone mean tristatic energy. So if you are warmer than the zone mean tristatic energy, you're going poleward, and if you are cooler, you're going equatorward. And this meridional wind on pressure levels gives us a mass flux that we can then integrate into a stream function. And this stream function gives us the thermally direct circulation when we use moist static energy, or theta E here. So what we have is two counter-rotating cells, one in each hemisphere. So basically, any heating that you see here is diabatic heating and diabatic cooling. And what you have is two counter-rotating cells clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. This includes the effect of eddies and moisture. There's also a parameterization of this circulation that was provided by Paul Louis et al. Not in 2008, in 2011 in this, or 2010. Would have to check that. But to be able to compute this stream function with not having to do the binning process that I had to do for this plot here. So it is much faster, and also allows an explicit separation between the mean and the eddy circulation. So we can keep only the eddy circulation in this stream function. And using this eddy mass flux that from the stem, we can get the polar heat transport by just multiplying it by the moist static energy and integrating it over all the moist static energy levels that we had. And this heat transport is going to be the exact same as I showed before by just integrating the polar heat flux, but through a different process. But what this allows us to do is to separate this heat flux into a poleward and equatorward heat transport by just defining two functions that are positive or zero when it's poleward or equatorward. So we can get a poleward and equatorward mass transport, F, by just integrating M times the indicator functions and doing the same for the heat transport. So we've got poleward and equatorward heat transport, so we can separate the two branches of this isentropic circulation. And because of mass conservation, we need to have the two mass transports to be equal and opposite. So we can just define a mass transport to be the mass transport in both of those branches to be F. And then we can then define an effective moist static energy. So it's going to be more of a dynamical moist static energy for each of those branches by dividing the heat transport of that branch by the mass transport. And this gives us an effective moist static energy there. And using this new formulation here for the heat transport, we can get a total heat transport by taking a difference between the two branches, which can be written as that here. And any change in H can then be written as a change due to the dynamics, with delta F being changed in the mass transport, and a change in the thermodynamics due to the thermodynamics. So changes in the effective moist static energy of each of the branches, or both of them grouped together. So as I said, we can separate the flow between an equatorward and poleward branch, and there's a large compensation in the polar heat transport between those two branches. In this plot here in bottom, what I show in black is the net eddy polar heat transport for a control experiment, which reaches about 5 petawatts, a little bit under 5 petawatts, around 45 degrees north. And then the blue and red lines are divided by 15 here to show, just shown the same graph. But they are the poleward eddy heat transport and the equatorward eddy heat transport. So there's a large cancellation between both of them. And then if we look at how polar heat transport responds to sea ice loss here in panel E, let's first just concentrate on the solid black line. This is a reduction in polar heat transport that I showed before with the other formulas, with the other diagnostic of PhD. And then by decomposing it into the dynamics and the thermodynamics part. So the dynamics here is the dashed dotted line here. It doesn't play a large role in response to sea ice loss. It is thermodynamics, the black dotted line, that plays the larger role. And in fact, it's the warming of the equatorward branch that is the dominant factor here. So what it means is that in response to sea ice loss, it's not a weakening of the eddies that creates this this reduction in eddy polar heat transport, but it is a warming of the equatorward branch. So a warming of the air that is coming back from the poles that increases the equatorward heat transport. And actually it's not a decrease in polar heat transport. It's just in the net that we see it like that.
2 minutes.
Yeah, thank you. And then in response to sea surface temperature increase, we've got the thermodynamics that play a larger role south of 4 degrees north, and north of that we've got dynamics that play a larger role. I didn't show the individual branches here because they are there's a large cancellation between both, and the response is just interesting when we look at the net for the thermodynamics here. So in summary, PMF experiments allow us to cleanly separate the effect of sea ice loss and sea surface warming on the atmospheric response. And sea ice loss and sea surface warming have a very opposite effect on the surface energetic response. One of them, so the warming is at opposite ends of the hemisphere. And the agreement between the models on the surface energetic conditions doesn't seem to have an effect on the agreement of the different models on the eddy polar heat transport. So the agreement is poor response sea ice loss for the surface MSC and DSC, but it's good for the transport of those quantities, or is better for transport of those quantities. And then, as I showed, so the response to the polar heat transport reduction that we see is actually an increase in equatorward heat transport due to that is thermodynamically driven. So the air returning from the poles is warmer than when we lose sea ice. And then response to sea surface warming, the thermodynamics dominate at lower latitude, and higher latitude, it's the dynamics that take over. So thank you very much. I'll be happy to answer any questions, either now or in the chat or by email. Thank you.
Thanks. So we have time maybe for a question. Looking in the chat. Give people a second to bring something up. So while we're waiting, I had a quick question. So the PA-MIP experiments that you're looking at,
yes,
they either apply sea ice changes or sea surface temperature changes.
Yes.
In the sea ice changes, is it just sea ice area loss, or do they also do something with the thickness of the sea ice?
So in the experiments I'm using here, it's just sea ice concentration that they change. They don't change the thickness in that one, but there's other experiments in the protocol that change the thickness to assess the effect of thickness changes.
Okay.
And I haven't done it for the analysis for thickness changes, but it would be interesting to see.
Yeah, that would be really interesting to see if you get the same response, or if there's, if it's all about the ice concentration or if thickness is playing some role.
Yeah.
Also. All right. I think we should move on. So again, put questions into the chat. So thanks for the great talk. And so our next speaker is Tyler Czrzanowski from Columbia. And Tyler, if you can share your screen.
Sure. Okay.
All right. I think we can see your
can you see
slide.
that okay?
Yep, I can see them. They look
Cool.
good. I'll give you a 10,
All right. Okay. All right. My name is Tyler Czrzanowski. I am a PhD student at Columbia. This work was done with my advisors, Mike Previty and Lorenzo Polvani, along with Gabriel Kyoto and Karen Smith. And I'm going to be showing how Arctic amplification can be considered a rapid response to radiative forcing. So Arctic amplification can be simply defined as enhanced Arctic surface warming. So in this plot, it's the change in surface air temperature averaged over the last 30 years of CMIP5 4 times CO2 simulations. you can see that the highest latitudes of the Arctic warm more than 14 degrees, and that warming is considerably less in mid-latitudes or tropics. You can also see that the latitudinal gradient is only apparent in the Northern Hemisphere and doesn't appear in the Southern Hemisphere, indicating that there's different physical processes at work in the Arctic versus the Antarctic. So Arctic amplification is thought to be caused by feedbacks and changes in heat transport. On the diagram on the left, it just shows various feedbacks and transports that have been implicated in either contributing to or opposing Arctic amplification. In this study, we specifically look at surface albedo, cloud feedback, water vapor and temperature feedbacks, as well as heat transport by the ocean and the atmosphere. And while there's a lot of debate as to what feedback or transport it contributes the most to Arctic amplification, I think it's important to note that these physical processes are operating on very different timescales. So something like the sea ice or ocean will respond over a longer time scale compared to something like the vertical profile of temperature in the Arctic, which can respond rapidly to radiative forcing. So we hope to answer a couple of questions. You know, how fast does Arctic amplification occur following 4 times CO2? And does the relative importance of the Arctic amplification mechanisms vary with time? You know, is it possible that what causes Arctic amplification in the initial response is different than, you know, once we're in a quasi-equilibrium situation? So to do this, we use simulations from 21 CMIP5 models. We use the fully coupled pre-industrial control and the above 4 times CO2 runs. So in those runs, CO2 is instantaneously quadrupled and they're spun off from the pre-industrial runs. We quantify the feedbacks using the radiative kernel method. A radiative kernel is the sensitivity of the top of atmosphere radiation to a change in some atmospheric field, like surface albedo or specific humidity. And the kernels that we use in this study are from CSM Cam5. We define the Arctic as being from 70 north to 90 north. This choice was convenient because this has about the same fractional area of land as the global average. We also calculated the atmospheric and ocean mixed layer heat convergence into the Arctic from changes in column energy content, as well as radiative fluxes that are output from the model. And you know, just to know, we're specifically looking at the mixed layer heat convergence here because ultimately Arctic amplification is surface warming, and the mixed layer will be the most influential part on surface warming. So we found that Arctic amplification appears very quickly following 4 times CO2, you know, within a few months. So in these plots, I just show the change in Arctic temperature and change in global average temperature. The solid line is the multi-model mean of the 21 models, and the shading indicates 1 standard deviation. You can see by the 3rd month, the Arctic temperature change has already begun to separate from the global average temperature change. You can also see the seasonality of Arctic amplification take shape within the 1st year, with a maximum in amplification in the cold season and minimum in the warm season. On the right, it's annual average change in temperature for the 150 years of the above 4 times CO2 runs. You can see for the first decade or so, temperature rises quite rapidly for both the Arctic and global average. And for the remaining 140 years, temperature rises at a slower rate as components like sea ice in the ocean adjust. We can actually quantify the amount of Arctic amplification using the polar amplification factor, or the PAF, and that's just defined as the ratio of the change in polar temperature to the change in global average temperature. And you know, in this plot, it just shows the annual PAF for 150 years. And you can see that in the first year, we already have a PAF of about 2.5, indicating that the Arctic has warmed, you know, 2.5 times more than the global average. You know, over the next decade or so, that increases to about 2.7, and you know, for the remainder of time, decreases to about 2.6. But it actually remains fairly consistent throughout the 4 times CO2 runs. There's not a lot of temporal variability in the PAF. We can also look at the vertical structure of warming following 4 times CO2. And at this point, we found it useful to define a couple of timescales that we would look at. The first being the first 3 months. And that was chosen because that's the point in which the Arctic change in temperature is significantly different from the change in global average temperature. We also looked at average over the first year, just so we capture an entire annual cycle, as well as the last 30 years, which is our quasi-equilibrium response, and that's comparable to what some other studies have looked at in Arctic amplification. So you can see, well, within the first 3 months that the latitudinal gradient in the Northern Hemisphere starts to form, and it's very much constrained to the surface. That because this is during polar night, the Arctic atmosphere is very stable, so that really traps the warming near the surface. When we look at the first year, we can see the center of warming move to north to be right over the pole. It's a little bit less well constrained to the surface, but the latitudinal gradient temperature strengthens. And by the time we look at the last 30 years, it's most of the Arctic warming is below 800 hectopascals, and the latitudinal gradient is most mature. So we showed that Arctic amplification is happening really fast when we quadruple CO2, and we want to know, what's contributing to this fast response. So when you just look at the radiative forcing from quadrupling CO2, that actually opposes Arctic amplification. So this plot just shows that the annual mean radiative forcing from this 4 times CO2. Because CO2 is going to absorb and emit more long-wave radiation when over places that are hotter, because they have more outgoing long-wave radiation, it actually selectively warms the tropics rather than the Arctic. And so this alone cannot explain the response that we're seeing. Not only that, but whatever feedbacks or transports that we see actually have to overcome this opposite latitudinal gradient from 4 times CO2. So what we did was we took all of these feedbacks and transports and we converted them to warming contributions to either the Arctic or global average. And we took the difference between them. And so anything greater than 0 means that that specific feedback or transport is contributing more warming to the Arctic than the global average. And that would be promoting Arctic amplification. And anything below 0 would be opposing Arctic amplification. I'm just going to go through the x-axis. P prime indicates the local deviation of the Planck feedback, which is basically a measure of how efficiently an area is cooling itself compared to the global average. That's followed by the lapse rate feedback, surface albedo feedback, water vapor feedback, the total cloud feedback, and the atmospheric and oceanic heat transport. You can see in the first 3 months, the only significant contribution to Arctic amplification is from the lapse rate feedback. In these plots, the dots indicate the multi-model mean, and the error bars are a 95% confidence interval from the 21 models. And you can see that, the lapse rate feedback is contributing about 0.5 degree more warming to the Arctic than the global average. You can also see that there's a small opposing contribution from the cloud feedback, which is selectively warming the global average over the Arctic. Now, things look a little bit different when we consider the first year. At this point, the Planck feedback and albedo feedbacks become important. And in fact, the albedo feedback becomes the dominant feedback producing this Arctic amplification that we see in the first year. At this point, the cloud feedback remains in opposition to Arctic amplification, and there's also a contribution to Arctic amplification from the ocean heat transport. In the last 30 years, the same 3 feedbacks are contributing to Arctic amplification, and it's mostly the albedo, followed by lapse rate, and then followed by Planck. We see that the water vapor and cloud feedbacks are opposing Arctic amplification. The atmospheric heat transport actually is opposing, it's by changing the meridional gradient and temperature that can produce a decrease in the atmospheric heat convergence into the Arctic. And, we find at this point that there's not a significant contribution from the mixed-layer heat convergence in the Arctic.
2 minutes.
Cool. So in conclusion, we found that Arctic amplification occurs rapidly, as in like within a few months when we quadruple CO2. And because of this, it's likely to be driven largely by atmospheric processes. And specifically, we found that this response in the first 3 months is driven largely by the lapse rate feedback. This is polar night, the albedo, there isn't incoming sunlight, the albedo feedback isn't important at this point. When we look instead at the first year or the last 30 years, we find that the albedo, lapse rate, and plank feedbacks are the main contributors. And those are, the feedbacks that are important in year 1 are the same feedbacks that are important when we look at our quasi-equilibrium response. Some good news that we draw from this is that because Arctic amplification happens so rapidly, it follows that if we were able to reduce the anthropogenic forcing from greenhouse gases, that we would expect potential for some near-term mitigation of Arctic warming, since the Arctic seems to respond very quickly to changes in forcing. And with that, I will take any questions.
Great, thanks. So any questions in the chat? I don't see any yet. So one quick thing. Oh.
There's one from Paul Kushner there.
Oh, sorry. Okay, from Paul Kushner. Nice talk. How do you think the warming in the first 3 months would look if you started the run in summer instead of January 1st? Would that affect your first 3-month feedback analysis?
Yeah, definitely. One of the takeaways from the study is that, the lapse rate is probably significant in the first 3 months because we're, quadrupling CO2 during polar night. And so, we're actually thinking of how that might be different if we quadruple CO2 in the other months. I think it's inherently a fast response, but I'm not sure if the feedbacks would stay the same.
So Yudong has a question. Great talk. Have you also looked at the kernel feedbacks over different timescales in Antarctica?
No, I have not looked. I have not used these kernels to look at any of the feedbacks or transports in Antarctica. That seems to be maybe, there's unfortunately, since there's not Antarctic amplification, it maybe doesn't have as much notorieties. But yeah, no, I think it'd be really interesting to see what kind of feedbacks are either, stopping Antarctic amplification from happening or suppressing it.
Great. So I think we need to move on, but there's more questions in the chat. And I'll just mention Dave Bailey notes that the CESM project is talking about running a series of COVID-related runs with decreases in emissions associated with COVID. So it might be interesting to see if, if this quick response in Arctic amplification, if there's anything that happens in those runs. So, and it's also just a note to everyone that we are thinking about doing some runs along those lines. Yeah. But there's other questions in the chat, so I encourage you to look at those. And we will move on to the last of our 15-minute talks. So Jiling Diao, who is going to share some work from the IHASP simulations, these high-resolution simulations on Antarctic conditions. So if you can share your screen and unmute, and we can see your screen.
Hear me?
Yeah, I think so. It sounds good.
Okay. Hi, good morning, everyone. Today I want to show some results of the colonials and the Antarctic slope current in long-term CESM IHASP simulation. Some preliminary result now. So the model we use is the CSM 1.3. So the land and the atmosphere resolution is 0.25 degree. The ocean and sea ice part is 0.1 degree with pre-industrial greenhouse gas forcing. This is a high resolution, fully coupled, and planned to run about 500 years. So this preliminary result is based on the first 320 years data. So our goal is to investigate the reasons for the intermittent occurrence of the motorized polonias, the Weddell Sea polonias, and the Antarctic slope current, and their influence on the Antarctic bottom water formation. So some background information. So in the Weddell Gyre, in the Weddell Sea region, the most dominant circulation is the Weddell Gyre. So there is a high eddy mixing at the eastern part of the gyre. When the flow go back to westward, this is a relatively warm flow. You can see it can pass both north and south of the motorized seamount. And here we focus on two kinds of polonia. The motorized polonia will form exactly above the motorized seamount. This is the satellite observation of the motorized polonias. And sometimes the motorized polonias can expand westward and form these huge Weddell Sea polonias. This is the satellite observation of the Weddell Sea polonia. In our simulation, sometimes the motorized polonia can be simulated very well. It's exactly about the motorized seamount. This is called the motorized polonia in the model. But sometimes the polonias will first occur about the Artstreet ridge region. So in this model, we call it the Artstreet ridge polonia. From the observation, so there is a high temperature band surrounding the motorized seamount. So this is also true in our model for both cases. This is due to the Taylor-Camp effect. So the warm water is westward flow. So the Taylor-Camp about the motorized seamount prevent the flow from going over it. So it must go surrounded it. So produce this halo structure or red or warm water. The difference is in ARP years about the Artstreet ridge. There is also a similar Taylor-Camp effect about the Artstreet ridge region. So this is the difference between these two cases. So for the salinity, the similar structure is also occurred, the Taylor-Camp effect about the motorized seamount, and similar Taylor-Camp effect about the Artstreet ridge for the ARP years. Here. So for the mixed layer depth, from the observation, there is also a shallower mixed layer surrounding the motorized seamount. So in our simulation, this structure can also be represented very well. There's a shallower mixed layer surrounding the motorized seamount here. So this figure shows the time series of the sea ice concentration and the mixed layer depth. First, we can see the sea ice concentration matched very well with the mixed layer depth. This means when polonias occurred, the deep convection event will follow. And you can see there is a clearly westward draft pattern for the Polonias, it first occurred at the Artstreet region and westward to the motorized seamount, and the motorized Polonias occur, and it became stronger, and then it will westward drop to the central Weddell Sea region. Sometimes the Weddell Sea Polonias will occur. And another feature is the Polonia event is periodically occurred through the time series. And this is the only data we have now for the 500 years. Due to the COVID-19, the data transfer have some problem. But from this data, we can see after 300 years, the Polonia event still occurred periodically. So this is a very good data for us to investigate the reasons for the intermittent occurrence of the Polonia event. And this is the sea ice vorticity. So from the observation, there's a high value band along the north and western bank of the motorized seamount. So in our model, this feature is also very clearly represented very well. Another feature is there seems like an eddy transport pathway through the high eddy activity at the eastern end of the Weddell Gyre to the Polonia event location. So this may be eddy transport pathway in this region. So we need to continue to explore this interesting pathway here. This is the donor velocity along the motorized section. So above is the left one is for the summer season. The right one is for the winter season. So we can say at the north flank of the motorized, there is a strong westward flow, and above it there is a in counterpart eastward flow above the motorized seamount. And it is stronger in the summer and a little weaker at the winter. So these are also represented very well. And another feature is this is the Antarctic slope current. So it can also captured in our model. This figure shows the relationship between the open ocean Polonias and the wind-related variables. So the color band is the Polonia event years. And we can say when Polonias occur, the SAM index would become, the value would become more bigger when the Polonias occur. Another variable is we treat the wind stress curve. The wind stress curve will become more negative when the Polonia event occurs. Notice that the value is reversed here. So this is from observation. And in our simulation, this is also true. So the gray color represents no Polonia years, and the yellow one represents the Weddell Sea Polonia, or even very huge imbibement here. And the blue and green represent the motorized Polonia and the Artstreet Ridge Polonia years. So we can say the positive wind stress curve anomaly matched with the no Polonia years, while the more negative wind stress curve anomaly matched with the Weddell Sea Polonia years. And the motorized Polonia and the Artstreet Ridge Polonia often matched with the transition between these two two cases. The SAM index is also true. When the SAM index is more smaller, it will correspond to no Polonian years, while if the value is more bigger, it will correspond to wet ocean Polonian years here. And finally, we will compare the Antarctic slope current for 3 cases. The left one is the fresh shelf. In this case, the Antarctic slope current is very strong, so the isocline will bend downward, so the warm water cannot go onto the shelf. So in this model, it can represent this case very well. And the second case is the dense shelf. In the dense shelf, the most dominant feature is the V structure. The V structure here, and the warm water flow can go transport onto the shelf due to some eddy activity here. In this model, this process can also be represented very well. The V structure isohaline and some warm water will be transferred onto the shelf. And the third case is the warm shelf. In the warm shelf, the warm water can go onto the shelf region. So in our model, this is also the case. The warm water can transport onto the shelf. So the conclusion is the CESM IHIS simulation can represent these processes very well, which is critical for the Antarctic bottom water formation, such as the telecamp effect about the motorized seamount and the Artstreet ridge. And the intermittency expansion of motorized polonias into the wet ocean polonias, and the 3 characteristic Antarctic slope current regimes can also be represented very well. And the wind stress curve anomaly and the SAM index are correlated with the occurrence of the wet ocean polonias. And this will be systemically be analyzed when the full 500-year data available, and we will continue explore the structure and the variables of the Antarctic slope current and its possible effect on the Polonia and Antarctic bottom water formation. This is mainly due to the shelf slope convection, and we will continue investigate the effect of the intermittent occurrence of the wet ocean polonias on the Antarctic bottom formation. This is mainly through the open ocean polonia convection given here. Thank you very much. Any questions?
Great, thank you. That was really interesting. And we have several questions in the chat, but I think we're running a little bit late. So in order to keep on time, I'd encourage you to answer the questions within the chat, because I see at least 4 of them, maybe 5 of them in there. Okay. So definitely a lot of interest in this work. It's great to see these results coming from the IHESP simulation. So thanks a lot. But we're going to need to move on to our lightning talks. And so Dave Bailey is going to take over in moderating those. So Dave, I'll hand it to you.
Yeah, okay, so I'm sharing my screen. I'll just say for the lightning talks, what I'm going to do is I'm just going to call on you by your given name, and then and there's one pre-recorded one here, I think, and then we will be giving you the 4-minute mark heads up that you've got a minute left to wrap up. Okay, so first up is Olivia. Olivia, can you unmute yourself? And you can tell me to advance the slides too.
Okay, will do. So hello, my name is Olivia Truex, and I'm a PhD student at the University of Otago, here to talk briefly about an ongoing project comparing proxy records of Antarctic climate variability with simulations from the CESM Last Millennium Ensemble. I'd like to start by thanking Betty Otto-Bliesner and Esther Brady for working with me on this project and virtually hosting me at NCAR these past few months. So my research aims to identify the drivers of last millennium cooling in the southern high latitudes by qualitatively comparing full and single forcing simulations from the last millennium ensemble to proxy reconstructions from Antarctica. To the left, I've shown a figure from Otto-Bliesner et al. 2016 outlining the initial states and simulation lengths of the LME control and forced runs. And to the right, I've included a recent compilation of temperature reconstructions from Antarctic ice cores by Stenny et al. 2017. These reconstructions show between 0.2 and 0.5 degrees of cooling across continental Antarctica over the last millennium. Now, previous research has attributed this cooling to increased volcanism, solar minima, and/or multicentennial trends in modes of atmospheric variability. But as of yet, there's not a widely agreed upon driver for last millennium cooling in the Antarctic within the paleoclimate community. So the most basic question is, does Antarctica get colder in the LME? Next slide, please. And broadly, the answer is yes. To the left, I've plotted the full forcing ensemble mean in 50-year average anomalies from the 1,000-year mean. And we can see a warm period from 850 CE to 1250 CE, which is followed by about half a degree of cooling and coldest temperatures after 1600. On the right, I've plotted annual average temperature between 60 and 90 degrees south. The full forcing volcanic only and solar only simulations are in gray with the ensemble mean in black. The timing of the 10 largest volcanic eruptions is denoted by the black bars. And so in the LME simulations, they indicate that large volcanic eruptions may cool the southern high latitudes strongly enough to force the Antarctic into a colder climate that persists after direct radiative forcing from volcanic aerosols dissipates. However, other forcings, such as solar minima, are necessary to produce the coldest temperatures seen after 1600. Next slide, please. And as we would expect, cooling is greatest over areas of the Southern Ocean with largest increases in sea ice area, indicating that ice-ocean feedbacks may have played an important role in sustaining a colder climate in the Antarctic in the decades after major volcanic eruptions. Next slide, please. However, we note that the forced cooling response in the LME shown on the left does not reflect the regional heterogeneity inferred from a compilation of proxy reconstructions shown on the right in a figure from Luning et al. 2019. Ice cores indicate that the Eastern Ross Sea bucked the last millennium cooling trend to warm over the last millennium. Next slide. We want to suggest that the homogeneous cooling in the LME may be due to the simulated dynamics of the southern annular mode. 20th century reanalysis indicates that a positive SAM cools the Eastern Ross Sea while a negative SAM warms the Eastern Ross Sea. A proxy-based SAM reconstruction by Datweiler et al. 2018, shown in the bottom left, shows a multicentennial trend to a more negative SAM between 1350 and 1800 CE, which could have acted to warm the Eastern Ross Sea against the backdrop of a continent-wide cooling trend. By contrast, in the last millennium ensemble, the SAM index remains semi-constant until a positive trend during the industrial period. This phenomenon has also been noted in other studies. Global climate models typically do not simulate the centennial trends in atmospheric dynamics inferred from proxy records. So to summarize, the LME simulates last millennium cooling in the Antarctic with all forcings and only volcanic forcing, but with a reduced magnitude for only volcanic. However, the LME does not simulate the SAM-like regional heterogeneity observed in proxy records. And I'm in the beginning stages of this work and my PhD. So I'd welcome any feedback or questions you have to offer via the chat, and I'll include my email in the chat. Thank you.
Great, thank you. And also note that, yeah, the questions go in the chat, please. Alex's is pre-recorded here, so I'm hoping that'll just work on its own. Alex was concerned about potential issues from her house, so
Hi, my name is Alexandra Yan, and I'm at the University of Colorado in Boulder. Today, I'm going to show you that forced changes in the Arctic freshwater budget emerged in the early 21st century. This work is currently under review in GRL and is funded by NSF. The work is motivated by observations of large changes in the Arctic freshwater storage, both the Arctic liquid and solid freshwater storage. The liquid freshwater storage has been increasing since the mid-1990s, which is shown in the figure here with the green stars. And this increase is relatively large, makes up about an increase of 10% in the liquid freshwater storage, or 10,000 cubic kilometers. The solid freshwater storage has decreased over the same time as the sea ice volume has decreased, but this increase in the liquid freshwater storage is more than just the melting sea ice, as the increase in the liquid storage is larger than the decrease in the solid storage. The oceanic gateway fluxes have not shown any trends over the period that they've been monitored, which is since the late 1990s for some, or in the 2000s for others. So the question that's been in the community is when we can actually expect to see a force signal emerge in the different parts of the Arctic freshwater budget, in particular because we know that there's large multi-decadal variability in terms of the Arctic freshwater budget. So to disentangle the forced response from this multi-decadal variability, we're using the CSM large ensemble, which is forced by the RCPA 8.5 into the 21st century, and the CSM low warming ensemble, which uses forcing that limits warming to 2 degrees by 2100 to answer this question. We're going to focus on two different terms to detect a forced response in the system. The first one is shift, which signifies when the first time that a freshwater term is outside the pre-industrial background variability as sampled in the 1,800 year-long control simulation from the CSM large ensemble. A stronger criteria, which really signifies the emergence into a completely different regime, is called emergence, which is when the simulated freshwater term stays outside the background variability until 2100. So the fluxes or variability in the storage shows no overlap with the pre-industrial variability. So using these two definitions, we can compile shift and emergence timing in different ensemble members for all the different terms of the Arctic freshwater budget, which is shown in the summary figure here. The thin bars signify the shift, the thicker bars, the emergence, which is what we're going to focus on right now. And then the two colors show the different scenarios to see if there's a scenario impact. If we focus on the earliest complete emergence in all ensemble members, we find that that actually occurs in the solid and liquid freshwater storage terms. And so that indicates that the observed increase in the liquid freshwater storage actually may already be a forced change as in the CSM. It's indicated that that emergence is complete before the year 2020. And we already know that there's a forced component for the solid freshwater storage, but for the liquid freshwater storage, so far that has been unclear. The earliest freshwater flux terms that show complete emergence in all ensemble members is the liquid Nares Strait freshwater export, followed by the liquid Davis Strait freshwater export about a decade later. And that those two have some overlaps, as you see Davis Strait's downstream of Nares Strait. And that's really interesting because Davis Strait has been monitored. There's been a gap of a couple of years now, but the monitoring is restarting this year. So if this is correct, we may actually be able to observe this in the future. And in terms of scenario impact, we see that emergence is only affected for two terms, the river runoff and the solid Fram Strait freshwater export, which shows emergence under the high warming scenario, but not the low warming scenario. So this is the summary of these three key points that I just showed you, more hopefully soon in the paper. Thank you very much.
Okay, I'm trying to get out of that. There it is. All right. Thanks, Alex. Sorry that my fan seems to be whirring away here, but next up, Abigail.
Yeah, thanks, Dave. Today I'm Abigail Smith at the University of Colorado Boulder, and today I'm going to be talking about some work that I've been doing with Alex Jan and Clara Burgard on detecting Arctic sea ice melt onset with a satellite simulator. Next slide, please. So why do we care about the melt onset? The melt onset and other seasonal transition dates can be used to evaluate how well climate models represent sea ice. So what I'm showing here is the average melt onset day over the satellite period for satellite data, the CESM Large Ensemble, and some CMIP6 models. And we see that the models, CMIP6 models included, show realistic but varying melt onset dates. And that these model differences in melt onset are unlikely due to internal variability alone. This paper is under review in the cryosphere discussions if you want more information on how we come to those conclusions. And we can use these differences to investigate other modeled sea ice characteristics, such as the ice area and the thickness. So it's a very useful metric. However, comparisons between climate models and satellite observations are indirect, and I'm going to talk a little bit about how. Next slide, please. So right now, melt onset products from satellite observations are taken from observed brightness temperatures. And brightness temperatures aren't currently simulated in climate models, including in the CESM2. So if we want to get melt onset from a climate model, we have to use standard model output and define it differently. So for example, with surface temperature. Next, please. So what we're actually doing here is using a satellite simulator to produce simulated brightness temperatures. And this opens up a whole new set of comparisons between the model and observations. The first comparison would be between these new simulated brightness temperatures and the observed brightness temperatures. And then we can also use the simulated brightness temperatures to create new simulated melt onset dates that should, in theory, be more comparable to the observed melt onset products. And so that's another new comparison. And then we can also compare the simulated sea ice melt onset dates from the brightness temperatures to those melt onset dates that we get from the standard model output. And next, please. Today, I'll just show some early results of these two comparisons circled. Next, please. So on the left, I'm showing the average brightness temperatures for June 2003 in the CESM2 and in satellite data. And we see from this kind of first cut that the simulator can produce realistic brightness temperatures for CESM2, so this is good. And on the right, I'm showing the CESM2 melt onset dates for 2003 using a kind of remedial definition of melt onset from the brightness temperatures, and as well as the melt onset definition from surface temperature. And so we see that they are similar based on what we would expect using the range we get with the CMIP6 models, but there are differences between these melt onset days. So by comparing the two methods of finding the melt onset, we can actually quantify the uncertainty introduced by differences in definitions between models and satellites. And I will stop there. Thanks.
Okay, great, thanks. Okay, Jennifer.
All right, can everyone hear?
Yep.
All right, so I am going to present actually on behalf of a larger effort going on in the Polar Climate Working Group to look at the influence of sea ice albedo on transient climate change. And here we're trying to argue potentially that there's a case for tuning the sea ice albedo. So there's a number of folks, but I put together the slides, so all credit goes to them and all errors go to me. Next slide. So the context here is obviously Arctic sea ice loss, large changes happening in the Arctic regions, and trying to simulate those in Earth system models. That's why we're all here. So here's the observed Arctic sea ice record. And Dave, can you just go to the next slide? Here's the CESM2. These are new results from the CESM2 large ensemble, but this is CESM2 CAM6. And basically what we see is that the observed sea ice has greater extent than CESM2 over the historical period, and that there's actually greater loss in the CESM2 than there is in the observed record. And we know this from special issue papers that have already been put out about CESM2 CAM6, in particular Patricia's. But here we really start to see the value of the large ensemble. There really are very few ensemble members that are overlapping with the observed record, and that makes us concerned about the representation of Arctic sea ice in CESM2. So next slide, Dave. So the question here is, should we street tune CESM2 sea ice? And I'll define what street tune is in a second, but I just want you to all remember the context here of CESM2 development, in particular the challenges that were occurring with the Labrador Sea and sea ice expansion in that region, and how there was very little interest project-wide in sea ice expansion and in tuning of sea ice after the CESM2 development. So if you go to the next slide, what really we're doing here is a street tune. So a street tune is tuning the car in its actual environment and during actual driving conditions. So the analogy here would be that the CESM2 has already been released, people are using it, they're driving it around, and we just want to come in and see if we can do a street tune to make the sea ice a little bit better in the Arctic. So Dave Bailey was really the architect of these changes. And Dave, if you could just advance one more forward. These experiments are really quite simple. They have two changes to the sea ice, one to the snow-green radius and the other to the melt onset temperature, but no other tuning was done in these runs. So this is basically a street tune of CESM2 with a couple of small changes to the sea ice albedo. So next slide. So here's kind of the punchline of what this street tune does. So we have, again, the CESM2 large ensemble in gray, the observations in red, and now we have 3 new lines on this plot, and then they're in the light blue, and then in the dark blue, they're ensemble mean. And so what we can see is that this new tuned ice small ensemble of just 3 has much more realistic aerial extent of the September sea ice, and the sea ice loss is now within the observed sea ice loss. The model and the observations are agreeing a lot better. So this is, I think, a success of the street tune. There's obviously a lot more to look into in this street tune.
1 minute.
Can you go to the next slide, Dave? I just want to highlight that one of the things that we think is really playing a role here is the sea ice thickness. And so this is just a nice figure from Patricia, just showing that the tuned runs have thicker sea ice. But the mean state is only one component of Arctic sea ice loss and Arctic warming. So I think there's a lot more to look into here. So last slide, it's the last one. So a summary, the CESM2 large ensemble simulations are confirming the CESM2 CAM6 historic Arctic sea ice loss is, is greater than observed. And I also encourage you to look at Patricia's paper. We know that sea ice mean state is one of many factors that can affect sea ice loss rates. So we did some street tuning, and so far we're seeing improved simulations in the Arctic. There are impacts outside of the Arctic, in particular the Antarctic sea ice also looks quite different. But I also want to highlight the initial results really here show modest non-polar impacts. So for example, the global mean surface temperature evolution looks pretty reasonable in these runs and not all that different than the CESM2. So if you have suggestions about things to look at in these runs, I'm happy to talk offline. Thank you.
Thanks, Jen. Okay, Mark.
Yep, can you hear me now?
Yes.
Great. So I'll be presenting work on the substantial 20th century Arctic warming caused by ozone depleting substances. This work was led by Lorenzo Polvani and was published earlier this year in Nature Climate Change. Next slide, please. So for those of you who are unfamiliar, ODSs are halogen gases containing chlorine and or bromine with the potential to break down ozone in the stratosphere. And we normally think of them used for refrigerants, air conditioners, stuff like that. And over the second half of the 20th century, their emissions rapidly increased until the introduction of the Montreal Protocol in 1987. And although they're much less abundant than CO2, on a molecule by molecule basis, they're really a potent greenhouse gas. And so on the right here is a figure of the radiative forcing, and the red is ODSs. So you can see that over this period, they are the second most important greenhouse gas after CO2. Next slide, please. So to explore the impacts of ozone depleting substances on the Arctic, we performed a set of simulations, 10 ensemble members, which are companion runs to the CSM large ensemble, where we fixed ODSs and ozone concentrations at 1955 values. So all other forcings were allowed to evolve as in the CSM large ensemble. And so by taking the difference of these 10 members and then the 10 members from a CSM large ensemble, we can isolate the difference due to ODSs. Next slide, please. So the main result here is that on the left is the forced historical warming over this time period in the 10 members of the CSM large ensemble, and there's about a 1.6 degree warming. And then when we keep fixed the ozone depleting substances and ozone, this forced warming reduces by about 50%. It goes down to about 0.8 in the Arctic. So these are really large effects we're seeing here. So one question you can have is how do we know this is due to the radiative effects of ODSs and not the effects on ozone? Next slide, please. So we performed another 10-member ensemble where we only fixed the ozone depleting substances, and we allowed the ozone to evolve as it does in the CSM large ensemble, and we got statistically kind of the same results as in panel B, where it was about reduced warming of about 50% compared to the historical runs. Next slide, please. So then along with this reduced warming due to ODSs being held fixed, we also see the sea ice loss being reduced by about a half as well. So this is September sea ice loss between 1955 and 2005, and you can see the reduction is about 50% as well. So these are really large changes due to ozone depleting substances. Next slide, please. So what are the key takeaways here? Although less abundant than CO2, ODSs are really potent greenhouse gases, and they can have very large effects in the Arctic. So in these runs in which we held ODSs fixed at 1955 values, the forced Arctic warming and sea ice loss were reduced by about a half. And we showed that this was due to the radiative effects of ozone depleting substances, not through their effects on ozone. And we all know that internal variability can be really large in the Arctic, but this signal is much larger. And so actually we could have done it with probably much less than 10 members. What I haven't shown you here is we did this with 2 different climate models. So we did it also with CSM Wacom, and you can see it in the paper for the further results there. And one nuance, which I really haven't mentioned, but I think it's important to take away.
1 minute.
These ozone depleting substances can have an outsized effect due to a large cancellation over this period between cooling from aerosols and warming from CO2. And there's the reference for that paper. Thank you very much.
Oh, thanks. Okay, this is a pre-recorded one from Ximing.
Good morning, everyone. I'm Ximing Xu from Tsinghua University.
Hold on.
Today, I'm going to talk about our recent efforts in designing a new grid hierarchy for ocean CS models and the implementation in CESM. So the new grid hierarchy consists of 3 traveler grids.
Sure why I'm not seeing it.
That are 0.45, 0.50, and 0.05 or 1/20th degree. So they target that climate simulation all the way to sub-mesoscale simulations. In the Arctic, which is the focus of our work here, the model grids are 22 kilometers. Good morning, everyone. I'm Xu from Tsinghua University in Beijing in terms of the resolution. With the CSM D-type experiments, in which the size 4 model.
Dave, yeah, I think it's the Finder that's still playing it. So open up the
the pilot floor.
With a reasonable CIS climatology.
Right there. Yeah, there we go. I apologize for that.
Good morning. I'm Tsinghua University in Beijing. Today I'm going to talk about our recent efforts in designing a new grid hierarchy for ocean CIS models and the implementation in the CESM. So the new grid hierarchy consists of 3 traveler grids that are 0.45, 0.50, and 0.05 or 1/20th degree. So they target that climate simulation all the way to sub-meso scale simulations. In the Arctic, which is the focus of our work here, the model grids are 22 kilometers, 7.3 kilometers, and 2.4 kilometers in terms of the resolution. With the CESM D-type experiments, in which the size 4 model is forced with core normal year forcing and coupled with slab ocean model, we are able to simulate a reasonable CIS climatology in the Arctic. And in specific, we have examined the CIS kinematics for high resolution runs and the scaling properties of the runs. And also we have examined the EVP convergence and the collateral effects on the Canadian archipelago and the landmass size simulations. So the grid system is openly available for the community to use. And also we have a ongoing geoscientific model development paper, which I show on the bottom right here. For the CIS kinematics, we have picked 2 days of different Arctic oscillation index on December 20th, which I show on the right, the deformation rate fields. This corresponds to a negative index. And then we can show that, we can see that the deformation fields are much finer and much and richer in structure for the high resolution runs, and which are arguably better as well. Because we have 3 resolutions and 3 consistent climatology, we are able to study the scaling. For example, on the left, we study the cumulative distribution of the total deformation. We show that by using the high resolution runs as a reference, we are able to evaluate the low resolution runs for their effective resolution, and we conclude that the effective resolution of the model is about 6 to 7 times coarser than the grid native resolution for simulating extreme or very large deformation events. And also comparing the 2 days, we show that the spatial scaling and the structural function, although they are on both days, they are multifractal and consistent with observations. There are drastic differences between the 2. So the Arctic oscillation or the forcing dependent scaling is witnessed here. For the EVP convergence, because we have a traditional EVP implementation in our model, we tend to see, for the simulation, we tend to see more subcycling of the EVP are needed for the higher resolution runs to attend a convergence or a kind of asymptotic behavior. This applies to the deformation PDF on the right, and also as well as the deformation instantaneous or daily deformation on the left, in which the non-convergent solutions are much noisier. And this doesn't really systematically shift the climatology, but for regions such as archipelago, due to the landmass ice dominance here in the winter, we show that the non-convergent, the convergence can systematically shift the ice thickness or ice volume here. The non-convergent solutions simulate thicker ice because of excessive noisy kinematic events, as well as thermodynamic response to it. So in this slide, we highlight that the EV convergence can have a big impact on the kinematics as well as the ice volume for landmass size. So the CIS, so the grid system is openly available for the public, and we want to hear from you the questions and comments, especially for the ongoing discussion paper. Thank you.
Okay, Yufei.
Okay, so can you hear me?
Yes.
Okay, thank you. Thank you, David. And good morning, everyone. This is Yufei from PNL. So today I want to give you a quick overview of our latest study about the technical action relationship between winter air stagnation and heat extremes in China with regional Arctic sea ice decline. And this work was funded by the US DOE and the NSF. And I want to thank all my research collaborators for their contributions to this work. So next slide, please. So as we know, the East China Plains area, or the ECP area, is one of the hotspot regions with severe air pollution, especially in winter. And this heavy air pollution can be attributed to three major factors. First is massive anthropogenic emissions, the rapid chemical formation, and also the unfavorable meteorological conditions. And here we mainly focused on the third part by investigating the possible relationship between regional air stagnation with global climate change, or specifically the Arctic change. To do that, we defined a so-called pollution potential index, or PPI, by weighted averaging the near surface wind speed and the air temperature gradient to describe the horizontal and vertical air pollutant dispersion capacity. And those numbers in the table on the lower right corner shows a good correlation between PPI and the major air pollution observations, suggesting PPI as a good proxy to describe regional air ventilation and regional air stagnation. And please note that the higher values in PPI suggest weakened air ventilation or stronger air stagnation. So next slide, please. So several recent studies have suggested a potential linkage between high latitude environmental change with medium latitude weather extremes. And our previous study has also reviewed a close relationship between PPI variations with Arctic sea ice change. So to understand the underlying dynamic processes, here we designed a series of climate sensitivity experiments by using a high top WACOM model under the CESM framework. So we run this model with climatological CIS and SST conditions for 30 years. And then we perturbed those CIS and SST over different Arctic regions with 2012 CIS and SST conditions with strong forcing. And please see those region definitions in the subplot B here down below. And the CDF curves on the right-hand side shows the modeling responses in terms of pollution favorable circulation pattern at 500 hectopascal and the ECP PPI indices. And we found the largest increases in both the probability and the magnitude in purple lines driven by the CS change over the R2 region, or the East Siberian and the Chukchi Seas. And those changes can be explained by an enhanced technical action pattern resembling the negative phase of the Eurasia pattern as shown in those contour lines in subplot C due to transient eddy vorticity forcing, and which significantly suppressed the East-Asia winter monsoon and enhanced the regional air stagnation extremes. So please see more detailed dynamic diagnosis in our manuscript. So next slide, please. And besides our own climate sensitivity experiments, we also examined the historical simulations and the future projections in CMAP6 model ensembles. And those time series shows a gradually increasing PPI along with a decreasing CIS in the 21st century. And this is more evident in those CDI curves in both P2 and P3 time periods. And I'm also showing you those model-specific results in the right table here. And though those numbers vary considerably, most models agree on a positive shift in in the PPI positive extremes. So next slide, please. So I just stop here with this schematic diagram, and please go to check our manuscript published in SAP for more technical details. And thank you for your attention.
Perfect. Well, thank you for such a wonderful session. We have gone 2 minutes over. I apologize for that. That's mostly me for the movie. Now we're scheduled for like a 10-minute break, and then we're due to come back at 12:20 for the individual working group lunch sessions. And so I'm just trying to find how to get back to the main screen again. Okay, I'm going to stop sharing. For those of you, you should have received the email invites to the individual working group lunch sessions. If you haven't received those, feel free to email me, and I'll also type Todd Amodeo's email in the little box here. Actually, Todd just did it. So email him if you have not received those invites. Otherwise, we'll see you back at about 12:20. Thanks very much for a nice session.
Yeah, on the separate Zooms. So just
on separate Zooms. Yeah. So thanks.